Welcome to Mechanics of Rest. Relativity has a strange reputation. People hear that time can slow down, that space can bend, that nothing can travel faster than light, and that a clock high above Earth does not tick at exactly the same rate as a clock on the ground. It can sound like science has stopped describing the real world and started speaking in riddles. But relativity is not magic, and it is not a theory built only for physicists. At its heart, it begins with a few simple questions. What does motion really mean? Why does light behave differently from everything else? Can two people disagree about time and both be correct? And if gravity is not just a pull, then what is it actually doing? In this episode, we will slow the whole idea down until the confusing parts begin to separate. No equations, no rushed explanations, just the story of how ordinary ideas about time, space, light, motion, and gravity slowly changed. If you enjoy long-form stories like this, a like and subscription helps Mechanics of Rest continue making these deep episodes every week. And while you listen, let us know in the comments where you are listening from. If there is a person, topic, story, or era you would like us to cover next, leave that there as well. To understand why Einstein's theory felt so strange, we first have to enter the world before it existed, a world where time seemed steady, space seemed fixed, and gravity seemed simple. Chapter 1: The Ordinary World Before Relativity. For most of human life, time seemed like the most reliable thing in the world. A day passed, a shadow moved, a clock ticked, and whatever else might be uncertain, time appeared to move forward at the same pace for everyone. A farmer in a field, a sailor at sea, a child watching a pendulum, and a scientist measuring the fall of an object could all assume that time itself was shared. It belonged to no one in particular. It stood behind events like a calm background, allowing one thing to happen before another, and allowing people to agree on when those things had occurred. Space seemed just as steady. A road kept its length whether someone walked along it or watched from a window. A table did not become shorter because a person passed beside it. The distance between two trees did not depend on who measured it, so long as the measuring was done carefully. This was the world ordinary experience gave to the senses, and there was nothing foolish about trusting it. At the slow speeds of human life, and under the gentle gravity of Earth's surface, space and time do appear separate, stable, and nearly universal. Motion also seemed easy to understand. If a cart rolled down a road, the cart was moving and the road was still. If a bird flew past the cart, the bird was moving faster. If someone threw a stone from the moving cart, the stone's speed could be understood by adding together the motion of the cart and the motion of the throw. These ideas were not just common sense. For many purposes, they worked. Bridges could be built, ships could be navigated, cannonballs could be aimed, planets could be tracked, and machines could be designed by treating time as a universal clock and space as a fixed stage. Long before Einstein, Galileo Galilei had already noticed that motion was suppler than it first appeared. A person inside a smoothly moving ship could drop an object and see it fall straight down, just as it would on land. A fly could move through the cabin without being left behind at the rear wall. The water in a vessel could behave normally. From inside the closed cabin, smooth, steady motion could be difficult to detect because everything inside shared that motion together. That insight matters because it loosened the simple idea that motion always had an obvious owner. A ship might be moving relative to the shore, but the person inside the ship could treat the cabin as their own resting world. The shore had one claim to stillness, the ship had another, and both claims could be useful depending on what was being measured. Galileo did not destroy ordinary space and time. He made motion relational, and that was the first quiet opening through which later physics would pass. Isaac Newton gave this older world its most powerful form. In 1687, his Principia described motion and gravity with a clarity that changed science for centuries. Newton's laws made it possible to explain why apples fell, why projectiles curved, why moons orbited planets, and why planets moved around the sun. His universe had space and time as separate, stable containers. Time flowed evenly everywhere. Space existed as a vast stage in which matter moved. Gravity acted as a force between masses, reaching across distance and shaping the motion of worlds. There was immense strength in that picture. Newtonian mechanics was not a crude guess waiting to be discarded. It was precise, useful, and repeatedly confirmed across ordinary scales. When a stone fell, when a pendulum swung, when a planet completed its orbit, Newton's framework gave answers of great accuracy. Even today, engineers and astronomers often use Newton's laws when the speeds are low and gravity is not extreme. The older theory remains one of the great working tools of science, because nature often allows simpler descriptions when conditions are gentle. A listener coming to relativity for the first time does not need to think of Newton as wrong in the ordinary sense. It is better to think of him as describing a broad, familiar region of reality with extraordinary success. His laws work so well in daily life that they train the mind to expect the world to be Newtonian everywhere. That training is part of why relativity feels strange. It does not begin by correcting obvious mistakes. It begins by finding the hidden limits of ideas that seem almost impossible to doubt. Through the 18th and 19th centuries, Newton's picture stood beside another growing branch of physics, the study of light, electricity, and magnetism. Light had long been difficult to classify. It behaved in some ways like a stream of particles, and in other ways like a wave. It could reflect from a mirror, bend when entering glass, produce colors, and travel across the emptiness between the sun and earth. Whatever light was, it clearly carried information across distance. It made the world visible, and yet it did not behave quite like a thrown stone, a rolling cart, or a falling apple. James Clerk Maxwell brought electricity, magnetism, and light into one theory in the 19th century. His work showed that changing electric and magnetic fields could sustain one another and travel as waves. When the speed of those waves was calculated, it matched the known speed of light. This was a deep unification in physics, but the important point for relativity is simple. Light seemed to have a speed built into the laws of electromagnetism themselves. It was not just another moving object whose speed could be added and subtracted in the ordinary way. That created a problem. In everyday experience, speeds add together. A person walking forward inside a moving train is moving faster relative to the ground than a person sitting still inside that train. A ball thrown forward from a moving cart has its throwing speed combined with the cart's speed, at least from the viewpoint of someone standing beside the road. If light behaved like those ordinary things, then its measured speed should change depending on how the observer moved. A beam of light measured while Earth moved toward it should seem different from a beam measured while Earth moved away. Physicists of the 19th century tried to preserve the older understanding by proposing the ether. The ether was imagined as a medium filling space, something through which light waves could travel, rather as sound travels through air or ripples move through water. If light was a wave, it seemed natural to ask what was waving. The ether gave an answer. It allowed scientists to picture light as a disturbance moving through a hidden substance spread across the universe. The idea was reasonable within the physics of the time. Sound needs air, water waves need water, and many scientists thought light must need its own medium. If Earth moved around the sun, then Earth should be moving through this ether. That motion ought to create a detectable difference in the measured speed of light, depending on whether the measurement was made along Earth's motion or across it. The effect would be small, but physics had become a science of small differences, measured with patient instruments. Albert A. Michelson and Edward Morley designed one of the most famous experiments in that older world. In 1887, they used an interferometer, an instrument that split a beam of light into two paths and then brought the beams back together. If one beam had taken slightly longer than the other because of Earth's movement through the ether, the returning light waves would show a shift in their interference pattern. The instrument was built to detect a very small change, the kind of change that would not be visible to the senses but might appear in carefully arranged light. The experiment did not give the expected result. The shift that should have revealed Earth's movement through the ether was absent. Light did not behave as the older picture required. Earth was certainly moving around the sun, and the sun itself was not fixed in any absolute human sense, yet the measurement did not show the ether wind that many physicists expected. The silence of the instrument mattered because it was not a failure of imagination. It was a measured absence produced by a device built for that specific purpose. At first, this did not mean that everyone abandoned the ether or Newtonian ideas overnight. Science rarely changes in such a clean way. Some physicists tried to adjust the ether theory. Hendrik Lorentz developed mathematical transformations that could explain why the expected effect might not appear. Objects moving through the ether, he suggested, might contract slightly in the direction of motion, and clocks might be affected in ways that hid the ether wind. These ideas preserved parts of the older framework, but they also made space and time less simple than they had seemed. The difficulty was becoming clearer. Newton's world treated time as universal, space as fixed, and motion as something measured against that background. Maxwell's light seemed to carry a speed that did not fit easily inside that world. Michelson and Morley had looked for evidence that Earth moved through the ether, and the instrument had not shown it. Lorentz had found mathematics that worked, but the meaning of that mathematics remained unsettled. This is why relativity did not arrive from nowhere. It grew out of a pressure inside physics itself. Ordinary experience still said that time was shared, space was steady, and speeds should add in the familiar way. Careful measurement was beginning to say that light obeyed a different rule. The older world had not collapsed because it still worked across almost everything people could touch, build, or see directly. But at the edge of precise measurement, one small fact refused to become ordinary. Light kept returning with the same speed. That single difficulty was enough to change the question. Instead of asking how light could be forced into the old structure of time and space, Einstein would ask what time and space must be like if light's behavior was taken seriously. The answer would not begin with black holes, warped universes, or distant galaxies. It would begin much closer to the ground, with clocks, motion, and the strange constancy of light. Chapter 2: The Strange Constancy of Light. Light seems familiar because life is built around it. It enters a room through a window, rests on the edge of a table, returns from a mirror, and gives shape to objects before the hand ever reaches them. A person does not need physics to know that light arrives, spreads, reflects, and disappears into shadow. For most of ordinary experience, light feels immediate. A lamp is switched on, and the room appears at once. Yet light is not immediate. It travels. The delay is usually too small for human senses to notice, because light moves so quickly that the distances of daily life almost vanish before it. Across a room, across a street, even across a city, the travel time is too brief to matter to the eye. The world seems to appear all at once because human distances are small compared with the speed of light. Precision, however, changes what can be noticed. By the 19th century, light had become one of the central problems in physics. It could be reflected and refracted, which made it behave like a ray. It could produce interference and diffraction, which made it behave like a wave. It brought heat from the sun, carried color from objects, and allowed astronomers to measure the heavens without touching them. Ordinary matter could be weighed, pushed, and placed on a table. Light resisted that kind of handling. It was everywhere in experience and difficult to fit into the familiar categories of matter and motion. James Clerk Maxwell gave light a new place inside physics. Working with electricity and magnetism, he showed that the two were not separate subjects joined only by convenience. A changing electric field could produce a magnetic field, and a changing magnetic field could produce an electric field. These linked disturbances could travel outward as waves. When Maxwell calculated the speed of those waves, it matched the measured speed of light closely enough to suggest that light itself was electromagnetic. The number was large enough to make human motion feel almost still. Light travels at about 299,792 kilometers per second in vacuum. At that speed, it can circle Earth more than 7 times in a single second if it had a path to follow around the planet. Sunlight takes a little more than 8 minutes to cross the distance from the Sun to Earth. Moonlight, reflected from the lunar surface, takes a little over 1 second to reach human eyes. These numbers give light a measurable life, even when the senses cannot feel its delay. Maxwell's theory did not simply give light a high speed. It gave light a speed that seemed to belong to the laws themselves. This was unlike a horse, a ship, a train, or a thrown stone. Those things had speeds that depended on the motion of the object and the motion of the observer. Light appeared in the mathematics of electricity and magnetism with a fixed value, as if nature had written that speed into the behavior of fields. That was the first pressure point. Older thinking still expected light to need a medium. Sound travels through air because air molecules compress and relax, carrying vibration from one place to another. Water waves move through water. A wave on a rope needs the rope. It seemed natural then to suppose that light waves must move through something as well. Physicists called this hidden medium the ether, and for a time it was not an absurd idea. It was a serious attempt to make light fit the known behavior of waves. The ether had to be strange. It had to fill space, pass through matter, allow planets to move, and carry light across enormous distances. It had to be stiff enough, in some sense, to transmit waves at tremendous speed, yet thin enough not to slow Earth as it moved around the Sun. These requirements made the ether difficult, but science often tolerates difficult ideas when they seem to preserve a useful structure. If light was a wave, and waves needed something to wave through, then the ether seemed to supply what was missing. Earth's motion made the ether testable. The planet travels around the Sun at roughly 30 kilometers per second. If Earth moved through the ether, then light measured along the direction of Earth's motion should behave slightly differently from light measured across that motion. The effect would not be large. Compared with light's speed, Earth's orbital speed is very small. But 19th century instruments had become good enough to search for small differences, and physics was learning to trust careful absence as much as obvious presence. Albert A. Michelson built an instrument designed for exactly this kind of delicacy. The interferometer split a beam of light into 2 beams, sent them along different paths, reflected them back with mirrors, and then recombined them. If one beam took a little longer than the other, the crests and troughs of the light waves would return slightly out of step. That mismatch would appear as a shift in the interference pattern. Instead of trying to see light's motion directly, the instrument allowed light to compare itself with light. In 1887, Michelson and Edward Morley carried out the experiment with great care. Their apparatus was mounted on a stone slab floating in mercury, allowing it to be turned smoothly. As the instrument rotated, one arm would line up differently with Earth's supposed motion through the ether. A shift in the pattern should have appeared as the orientation changed. The expected ether wind did not show itself. The result was not zero in the loose sense of an experiment badly made. It was close enough to zero to become a problem. The plain meaning was difficult to accept. Earth was moving through space, yet light did not reveal that motion in the expected way. The measured speed of light did not seem to change as it should have if the ether behaved like a medium at rest. Something in the old arrangement was wrong, but the exact mistake was not immediately obvious. Many physicists did not rush to throw away the ether. They tried to repair the theory, as careful scientists often do when a familiar framework meets an unwelcome measurement. Hendrik Lorentz offered one of the most important repairs. He proposed that objects moving through the ether might contract slightly along the direction of motion. He also developed transformations that adjusted measurements of space and time in ways that preserved the form of Maxwell's equations. These transformations worked mathematically. They could explain why the Michelson-Morley experiment failed to detect the ether wind. Yet in Lorentz's interpretation, the ether still remained underneath the picture, hidden but present. This left physics in a peculiar position. The mathematics was beginning to treat space and time as flexible, but the interpretation still tried to keep the older background. Clocks and rulers were being adjusted to save the fixed speed of light, while the ether remained as a kind of invisible stage. The adjustments were clever, and some of them would survive inside relativity, but their meaning would change. A mathematical patch can work before anyone understands what it is really saying. Einstein's move was quieter and more radical. He did not begin by asking how Earth moved through the ether. He began by taking seriously two ideas that had already been pressing against each other. The laws of physics should be the same for observers moving steadily relative to one another. The speed of light in vacuum should be the same for all such observers, no matter how the source or observer moves. Those two statements sound simple, but together they change the meaning of time and space. The strangeness comes from the second statement. If a person throws a ball forward from a moving train, someone standing on the ground measures the ball's speed as the speed of the train plus the speed of the throw. This agrees with ordinary experience. If the same person switches on a lamp at the front of the train, older intuition expects the light to behave in some similar way. Perhaps the train's motion should add to the light's speed, at least for someone standing beside the track. Relativity says it does not. The light is measured at the same speed. A slow example helps soften the difficulty. Suppose two people measure the same beam of light. One is standing on a platform. The other is moving smoothly in a train. Their ordinary measurements of distance and time will not agree in the old way, because if they did, they would measure different speeds for light. To keep light's speed fixed for both of them, something else must give. That something is not the light. It is the way space and time are divided between observers. This is where relativity begins to feel unlike common sense. The mind wants one master clock and one master ruler behind the world, silently correcting everyone's local measurements. It wants to say that one observer is really right and the other is only confused. But the fixed speed of light does not leave room for that older comfort. If light's speed is the same for observers in steady relative motion, then time and distance cannot be universal in the simple Newtonian way. The result is not chaos. Relativity does not say that anyone can measure anything and be equally correct. It gives strict rules for how different observers' measurements relate to one another. The disagreement is lawful. A moving clock, a moving ruler, and a moving observer all belong to a structure in which light keeps the same speed. What changes is not the seriousness of measurement, but the assumption that time and space exist as separate, identical backgrounds for all observers. Light therefore became more than a visible thing. It became the clue that forced physics to revise its deepest habits. Maxwell had shown that light belonged with electricity and magnetism. Michelson and Morley had shown that the expected ether wind was not there. Lorentz had found mathematical adjustments that hinted at flexible space and time. Einstein would remove the hidden ether from the center of the explanation and let the constancy of light stand openly. From that point, the next difficulty follows naturally. If light's speed is fixed for observers who are moving relative to one another, then those observers cannot always agree about timing. Events that seem simultaneous from one frame of reference may not be simultaneous from another. This is the first truly unsettling step in special relativity, because it reaches into one of the simplest assumptions people make about the world, that when two things happen at the same time, everyone should be able to agree that they did. Chapter 3: Einstein and the moving train. Albert Einstein did not begin relativity by trying to make the universe sound strange. He began with a difficulty that had become hard to ignore. The laws of electricity and magnetism said that light had a fixed speed, and careful experiments had failed to show the ether wind that older physics expected. The problem was not that science had no facts. The problem was that the facts did not sit comfortably inside the old picture of time, space, and motion. In 1905, Einstein was working at the Swiss Patent Office in Bern. He was not yet the public figure whose name would later become almost inseparable from genius. His daily work involved examining inventions, many of them concerned with electrical devices, clocks, and systems for coordinating time. Outside that official work, he was thinking about physics with unusual patience. The question that mattered to him was not how to save every inherited assumption, but how to state the situation as simply as possible and then accept what followed. Special relativity rests on two main ideas. The first says that the laws of physics are the same for all observers moving steadily relative to one another. A person in a smoothly moving train can carry out physics inside the carriage and find the same laws as a person standing on the platform, as long as the train is not speeding up, slowing down, or turning. This is close to Galileo's older insight, and it agrees with ordinary experience. Smooth shared motion does not announce itself from inside. The second idea is the one that changes everything. Light in vacuum has the same speed for all such observers. It does not matter whether the source of light is moving toward someone, away from someone, or sideways relative to someone. The measured speed of light remains the same. This is the part that ordinary experience does not prepare the mind to accept, because nearly everything in daily life seems to have speeds that add or subtract. A train makes the problem clear because a train belongs to ordinary experience. A passenger walking forward inside the carriage has one speed relative to the train and another speed relative to the ground. If the train moves at 50 kilometers per hour and the passenger walks forward at 5 kilometers per hour, a person on the platform can describe the passenger as moving at 55 kilometers per hour. No deep mystery appears. The motion of the passenger and the motion of the train combine in the expected way. Light refuses to join that pattern. If a lamp is switched on inside the moving train, the light does not gain the train's speed for the observer outside. The passenger and the person on the platform still measure light at the same speed. The mind wants to pause here and object, because the statement feels as though it has broken a rule. In truth, it has broken only a rule borrowed from slow objects. Balls, footsteps, carts, and trains belong to the ordinary range of speed, where the difference is too small to reveal the deeper structure. Einstein's genius in this moment was partly an act of restraint. He did not add another hidden mechanism beneath the ether. He did not keep one master clock behind the universe and treat all other clocks as imperfect. He asked what the world must be like if both principles were accepted together. The laws of physics stay the same for steady motion. Light's speed stays the same for all steady observers. Space and time must then adjust around those facts. The famous train and lightning thought experiment begins with a simple scene. A train moves along a track. A person stands at the middle of the train. Another person stands on the platform beside the track. Lightning strikes the front and back of the train, leaving marks at both ends. The platform observer is positioned midway between the two strike marks on the ground, and if light from both strikes reaches that observer at the same moment, the platform observer says the strikes happened at the same time. Inside the train, the situation is different. The person at the middle of the moving train is moving toward the place where the front strike happened and away from the place where the rear strike happened. Light from both strikes travels at the same speed, but the train observer meets the light from the front strike sooner because the observer is moving toward it. Light from the rear strike has farther to catch up. From the train observer's measurements, the two flashes do not arrive together. The ordinary mind wants to solve this by saying that one observer must be wrong. Perhaps the platform observer saw the true timing, while the train observer was misled by motion. Einstein's answer is more careful. Each observer is allowed to correct for the travel time of light within their own frame of reference. When that correction is done properly, the disagreement remains. Two events that are simultaneous for the platform observer are not simultaneous for the train observer. This is the relativity of simultaneity. It does not say that reality is confused or that events happen in any order someone prefers. It says that simultaneity, the judgment that two distant events happened at the same time, depends on the observer's state of motion. Nearby events are easy. If two sparks occur in the same place at the same time, observers can agree on that meeting. The difficulty appears when events are separated by distance, because information from those events must travel, and light's speed is finite and fixed. The idea becomes gentler when it is separated from drama. Nothing mystical happens to the lightning. Nothing strange is felt by the passengers. The platform remains ordinary. The train remains ordinary. What changes is the comparison between distant events. To say that two separated things happened at the same time is not as simple as ordinary language makes it sound. It requires a method for synchronizing clocks and accounting for the travel of light. Clocks are central here. Before relativity, it was natural to imagine that all good clocks could, in principle, be set to one universal time. If they disagreed, the problem belonged to the clocks, not to time itself. Einstein treated clock synchronization as a physical procedure. Signals had to move between clocks. Observers had to decide how those signals were used. Because no signal could outrun light, the way clocks were synchronized became part of physics rather than a mere technical detail. This is one reason the patent office background is often mentioned, though it should not be turned into a legend. Einstein lived in an age when railways, telegraphs, electrical networks, and public clocks had made time coordination a practical matter. Modern societies needed clocks to agree across distance. Physics needed the same thing with greater precision. The question of what it means for distant clocks to be synchronized was not just philosophical. It touched instruments, signals, and measurement. Einstein's 1905 paper, usually translated as On the Electrodynamics of Moving Bodies, did not begin with grand language. It moved through definitions, observers, rods, clocks, and light signals. The surface was technical, but the central movement was plain. If the speed of light is the same for observers in steady motion, then measurements of time and space must depend on the observer's motion. What had seemed universal becomes relational, but not arbitrary. The word relational is important. Relativity is often misunderstood as saying that everything is merely a matter of opinion. That is not what it means. A platform observer and a train observer may disagree about whether distant events were simultaneous, but their disagreement follows precise rules. Each can translate the other's measurements into their own frame. The world has not become loose. It has become structured in a way that ordinary intuition did not expect. For a tired listener, perhaps the simplest way to hold the thought is this: the speed of light is the fixed part, and time and space become the adjustable parts. Ordinary life teaches the opposite. It teaches that time and space are fixed, while speeds vary. Special relativity reverses that expectation. Because light keeps the same speed, observers in different states of motion divide time and distance differently. The train example also shows why relativity had to be discovered through thought as well as machinery. The Michelson-Morley experiment had placed a measured difficulty before physics. Maxwell's theory had supplied the constant speed of light. Lorentz had written transformations that helped preserve the mathematics. Einstein took those pieces and changed their meaning. He did not treat the strange behavior of light as an effect to be hidden by contraction through an ether. He treated it as a clue about the structure of measurement itself. Once simultaneity changes, time cannot remain untouched. If two observers disagree about whether distant events happen together, then their clocks cannot belong to one universal ordering in the old sense. This does not mean that clocks stop working. It means they work locally inside frames of reference, and their relation to other clocks depends on motion. The familiar clock on the wall, the clock in a moving train, the clock in an aircraft, and the clock in a satellite all remain real clocks. They simply do not all belong to one shared flow in the way Newton's world assumed. From here, the next step is unavoidable. If time itself depends on motion, then a moving clock must be compared differently with a clock at rest. The change is too small to feel on a train and far too small to notice in a walking body, but at high speeds and with precise instruments it becomes measurable. Relativity begins by unsettling simultaneity, and then it moves inward toward the ticking of the clock itself. Chapter 4: How Time Slows Down. A clock seems like a simple object because its purpose is so familiar. It divides the day into equal pieces, gives names to hours, and lets one person agree with another about when something happened. A clock on a wall, a watch on a wrist, a clock inside a phone, and an atomic clock in a laboratory all seem to serve the same deeper thing: time itself. The machine may be more or less accurate, but ordinary thought assumes that all good clocks are trying to measure one shared flow. Special relativity changes that assumption gently but completely. It does not say that clocks are useless, or that time is imaginary, or that everything becomes uncertain. A clock still measures time. It measures the time along its own path through the world. When two clocks move differently, especially when one moves very fast compared with the other, they do not have to agree after they are brought back together. The disagreement is not caused by bad machinery. It belongs to the structure of motion, light, and measurement. The simplest way to see this is through a light clock. The clock does not need gears or hands. It can be imagined as two mirrors facing each other, with a pulse of light bouncing between them. One tick happens when the light travels from one mirror to the other and back again. If the clock is resting on a table, the light moves straight up and straight down between the mirrors. The distance is fixed, the speed of light is fixed, and the tick has a definite duration. Now let the same clock move smoothly sideways. From the point of view of someone moving with the clock, nothing strange happens. The mirrors remain one above the other. The pulse of light still travels between them. Inside that moving frame, the clock ticks normally because everything needed to define the clock is moving together. The person beside it has no local sign that their own time has become abnormal. From the viewpoint of someone watching the clock pass by, the light takes a different path. While the light travels upward from the lower mirror to the upper mirror, the clock itself moves sideways. The pulse therefore traces a diagonal path rather than a straight vertical one. The same thing happens on the way back down. The light has farther to travel between ticks, not because the mirrors changed in their own frame, but because the whole clock is moving across the observer's view. Light cannot speed up to make up the extra distance. That is the crucial point. If the speed of light is the same for both observers, and the outside observer sees the light travel a longer path, then the tick must take more time according to the outside observer. The moving clock runs slowly compared with the outside clock. Nothing inside the moving clock feels slow. The slowness appears only when one frame compares its clock with another. This is time dilation. The phrase can sound dramatic, but the idea is precise. A moving clock measures less elapsed time between two shared events than a clock that stayed in the other frame when the clocks are compared under the right conditions. The difference is tiny at everyday speeds. A car, a train, or an aircraft does not move fast enough for human senses to notice it directly. At ordinary speeds, Newton's old picture remains an excellent approximation, and the world feels as if all clocks share one time. At higher speeds, the effect becomes too large to ignore. Particles called muons provide one natural example. Muons are produced high in Earth's atmosphere when cosmic rays interact with atoms there. In their own rest frame, muons decay very quickly, so quickly that many should not survive long enough to reach the ground if ordinary Newtonian time were the full story. Yet many do reach detectors near Earth's surface. From Earth's frame, their high speed makes their internal clocks run slowly, allowing them to travel farther before decaying. The muon does not feel like it has been granted extra time. In its own frame, its lifetime remains normal. The explanation depends on comparing two descriptions of the same physical process. From Earth's frame, the muon's time is dilated. From the muon's frame, the distance through the atmosphere is contracted. Both descriptions agree about the final measurable fact. Muons arrive at the ground in numbers that would otherwise be difficult to explain. Laboratory experiments made the effect more controlled. Particle accelerators can move particles at speeds close to the speed of light, and their lifetimes change in exactly the way special relativity predicts. A particle that would decay quickly at rest can survive longer when moving rapidly through a detector. This is not an impression, and it is not a philosophical reading of time. It is measured through tracks, decay products, detector signals, and repeated counts. Human clocks have also been tested. In 1971, Joseph Hafele and Richard Keating carried atomic clocks aboard commercial airliners flying around the world. Other atomic clocks remained at the United States Naval Observatory. When the traveling clocks returned, they were compared with the clocks that had stayed behind. The differences were small, measured in nanoseconds, but they were real and broadly consistent with relativistic predictions once both motion and gravity were included. The airplane experiment is useful because it brings relativity into a range of motion that still feels human. The planes did not travel anywhere near the speed of light. Passengers could sit, eat, read, and sleep, while the clocks beside them accumulated tiny differences. The effect was far too small for ordinary life, but atomic clocks are not ordinary senses. They can measure intervals so finely that the hidden structure of time becomes visible where a human body notices nothing. There is a quiet lesson in that. Relativity often feels strange because people expect a theory to change experience directly. But many physical truths remain invisible until instruments become sensitive enough to reveal them. Air pressure existed before barometers. Germs existed before microscopes. The slow disagreement between moving clocks existed before atomic timekeeping. Instruments do not create the effect. They give it a measurable surface. Time dilation also appears in a famous form, sometimes called the twin paradox. One twin remains on Earth, while the other travels in a very fast spacecraft and later returns. The traveling twin has aged less. The word paradox can make the situation sound like a contradiction, because from the traveler's point of view, it might seem that Earth was the one moving away and coming back. The resolution lies in the fact that the traveler changes frames when turning around, while the stay-at-home twin does not undergo the same history of motion. Their paths through space-time are different, and different paths can contain different amounts of elapsed time. This is one of the places where relativity becomes easier, when time is treated less like a universal river and more like something measured along a path. A clock does not merely sit inside time. It carries its own record of time along its motion from one event to another. Two clocks can leave the same place, follow different paths, and meet again with different readings. The readings are not opinions. They are physical records of different journeys through space-time. At slow speeds, these differences are so small that they disappear into practical life. Two people walking through a house do not return with meaningfully different ages. A train journey does not make a passenger noticeably younger than someone on the platform. Even an airplane flight changes elapsed time by an amount far below the scale of ordinary memory. The reason common sense feels so stable is that daily life occupies only a very narrow region of what nature allows. Relativity did not ask people to abandon common sense where common sense works. It asked physics not to mistake that limited region for the whole universe. Near the speed of light, the old habits fail. With precise clocks, even modest speeds can leave small traces. Motion changes the comparison between clocks because the speed of light remains fixed, and the geometry of measurement adjusts around that fact. A moving clock, then, is not broken. It is not being tricked by motion. It is doing exactly what a clock does, measuring the time along its own path. Another clock, on another path, may measure a different amount. The difference may be tiny, or it may be large, depending on the motion involved. Each clock remains faithful to its own route through the world. Once this is understood, time is no longer the same background it was in Newton's universe. It becomes connected to motion. It becomes something that can be compared only with care. The clock in the train, the clock on the platform, the clock in the aeroplane, and the clock inside a particle accelerator all belong to the same lawful structure, but they do not all have to keep one universal rhythm. This change in time cannot happen alone. If observers moving relative to one another measure time differently, then their measurements of distance must also adjust. Light's speed remains the fixed quantity that binds the comparison together. A slower clock and an unchanged light speed lead naturally to a changed measurement of length, and the next part of relativity begins with that quieter, stranger consequence. Chapter 5. Why distance changes with motion. Distance feels even more solid than time. A clock may seem delicate, but a ruler feels plain. It can be held in the hand, laid against a table, placed beside a doorframe, or used to mark wood before it is cut. If a road is 5 kilometers long, ordinary thought expects it to remain 5 kilometers long whether a person walks along it, cycles beside it, or watches it from a moving train. Length appears to belong to the object itself. Special relativity changes this idea because time cannot change alone. Once the speed of light is fixed for observers in steady relative motion, and once moving clocks are measured to tick differently, distance must also become part of the adjustment. Speed is distance divided by time. If light speed is to remain the same for observers who disagree about time, then their measurements of distance cannot remain identical in every frame. The two ideas are tied together more closely than ordinary experience suggests. This is where length contraction enters. It means that an object moving relative to an observer is measured as shorter along the direction of its motion. The shortening is not visible at daily speeds, and it does not happen in every direction. A train moving along a track would be measured as contracted along the track, not squeezed downward into the rails or narrowed across its width. The effect belongs specifically to the direction of relative motion. At first, the idea can sound like a physical crushing. That is not the right picture. A person sitting inside the train does not feel the carriage shrink. The seats do not press together. The windows do not close inward. The walls do not scrape the passengers. In the train's own frame of reference, the train has its normal length, and a ruler carried inside it gives the same local measurement it always did. The contraction appears when another observer measures the moving train from a different frame. A person standing beside the track using synchronized clocks in the platform frame measures the position of the front and back of the moving train at the same platform time. That requirement matters. To measure the length of a moving object, the observer must mark both ends at the same time in their own frame. But Chapter 3 has already loosened simultaneity. What counts as the same time for the platform does not have to count as the same time for the train. Length contraction therefore grows naturally from the relativity of simultaneity. Measuring the length of a moving object is not as simple as putting a ruler beside a still table. The front and back of the object are in different places, and those places must be recorded together according to some clock system. Since moving observers disagree about distance simultaneity, they also disagree about the length measured between simultaneous endpoints. Distance has entered the same relational structure as time. Hendrik Lorentz reached part of this result before Einstein gave it its later meaning. Lorentz was trying to explain why experiments such as Michelson and Morley's had failed to detect Earth's motion through the ether. If objects moving through the ether contracted in the direction of motion, then the expected shift in the light pattern might disappear. In Lorentz's version, contraction was still tied to motion through a hidden medium. It was a physical adjustment that helped protect the older ether picture. Einstein kept the mathematical structure but changed the interpretation. No hidden ether was needed. Length contraction did not happen because an object was being pressed by motion through an invisible substance. It happened because different observers, moving relative to one another, divided space and time differently while still agreeing on the speed of light. The same formulas could remain, while their meaning moved into a cleaner and more direct view of measurement. The easiest slow example is a spacecraft passing Earth at very high speed. From Earth's frame, the spacecraft is shorter along its direction of travel than it would be when resting beside Earth. From the spacecraft's own frame, the spacecraft remains normal, while Earth and the distance ahead are the things moving past. Each frame has its own consistent measurements. Neither observer sees their own ruler shrink. The contraction belongs to how one frame measures an object moving through it. This can feel like a disagreement that should be impossible. If Earth says the spacecraft is shorter, while the spacecraft says it is not, then ordinary instinct wants a final judge. But relativity does not provide a hidden preferred frame where the true length waits untouched. Instead, it provides a rule for translating one observer's measurement into another's. Proper length, the length measured in the object's own rest frame, is one quantity. Contracted length, measured from a frame in which the object is moving, is another. The word proper can be helpful if it is treated gently. The proper length of a ruler is the length measured by someone at rest with that ruler. That is the longest length other inertial observers will assign to it. A moving observer who measures the ruler from the side will find it shortened along the motion. The ruler itself has not lost its reality. It has acquired different measured lengths depending on the relationship between ruler and observer. This is not because measurement has become careless. It is the opposite. Relativity appears when measurement becomes exact enough to ask what must be done to measure a moving thing properly. Where are its two ends? At what times are those end positions recorded? Which clocks are being used? How were those clocks synchronized? Each question that ordinary life ignores becomes important when motion approaches the speed of light. A road gives a simple way to hold the idea. Imagine a very fast traveler crossing a long distance between 2 points. From Earth's frame, the distance between those points may be large. From the traveler's frame, because the traveler is moving relative to Earth, the distance ahead is contracted. This helps explain the muon example from the previous chapter. From Earth's frame, fast muons live longer because their internal clocks are time-dilated. From the muon's frame, they do not need extra time in the same way because the atmosphere's thickness along their path is contracted. 2 descriptions, 1 outcome. That phrase is useful, though it should not be made into a slogan. Earth says the muon's clock runs slow, allowing it to survive long enough to reach the ground. The muon's frame says the distance to the ground is shorter, so the trip can be completed within its normal lifetime. Both descriptions agree on the event that matters. The muon reaches the detector. Relativity keeps the final meeting of events stable, while allowing time and distance measurements to differ between frames. Length contraction also shows why relativity is not merely about clocks. If time dilation were the only effect, light's fixed speed would become impossible to preserve consistently. Distance must shift because speed involves both distance and time. The old Newtonian world allowed time to remain universal, while motion was added and subtracted against that background. Einstein's world keeps light fixed and lets space and time share the burden of comparison. The effect becomes stronger as speed increases. At ordinary speeds, the contraction is so tiny that no ruler in daily use could reveal it. A moving car does not become noticeably shorter to someone standing beside the road. A passenger train does not shrink in any practical sense as it passes the station. Even fast aircraft move too slowly for length contraction to matter in ordinary engineering. Relativity is not hidden because it is rare. It is hidden because human life moves through a very slow corner of the possible range. Near the speed of light, the difference grows large. A spacecraft moving at a substantial fraction of light speed would be measured from Earth as significantly shortened along its direction of travel. Inside the spacecraft, nothing would feel compressed. The crew would measure their own cabin, instruments, and distances normally. Looking outward, however, they would assign contracted distances to the space they were crossing. Each perspective remains orderly inside its own frame. The deeper adjustment is not that objects secretly change shape in one absolute way. It is that length is no longer independent of motion. Just as there is no single universal time shared by every moving observer, there is no single universal length assigned to a moving object by all observers. The measurements are not random. They are bound by exact relationships, and those relationships protect the constancy of light. Minkowski would later express special relativity through spacetime, joining space and time into a single geometric structure. In that view, time dilation and length contraction are not separate tricks. They are different faces of the same underlying relation between observers moving through spacetime along different directions. A clock measures time along its path. A ruler measures distance within a frame. Motion changes how those measurements divide the shared structure into space and time. For a listener meeting this for the first time, it may be enough to keep the simplest chain in mind. Light has one fixed speed for all steady observers. To make that possible, observers in relative motion cannot all agree on simultaneity. Since measuring the length of a moving object requires judging where both ends are at the same time, disagreement about simultaneity leads to disagreement about length. Distance changes with motion because time, distance, and light are woven together. Nothing in this chapter requires ordinary objects to behave strangely in daily life. Tables remain useful. Roads keep their measured lengths for people at rest with them. Trains arrive at stations without needing relativistic correction. The older world continues to work wherever speeds are low and measurement does not reach the hidden differences. Relativity waits underneath, becoming visible when the speed is high enough or the instrument careful enough. Once distance and time have both changed, special relativity has altered the foundations. It has shown that clocks and rulers are not absolute in the older sense. It has kept the laws of physics consistent for steady motion. It has protected the fixed speed of light by asking space and time to adjust around it. The next consequence reaches into matter itself, where mass and energy turn out to be linked more closely than ordinary experience could have guessed. Chapter 6. The mass, the energy, and the hidden exchange. Mass feels like one of the most ordinary properties of matter. A stone has more mass than a feather. A full cup has more mass than an empty one. A body resists being pushed. A planet holds other bodies near it through gravity, and a scale gives a number that seems to belong to the thing being weighed. In daily life, mass feels like substance itself, the amount of material present in an object. Energy seems different. It appears as motion, heat, light, electricity, sound, and chemical change. A moving wheel has energy because it can do work. A warm surface has energy because its particles are moving internally. A charged battery has energy because it can drive a current. These forms can change into one another, and 19th century physics had already learned to treat energy as something conserved through transformation. But mass and energy still seemed like different kinds of accounting. Special relativity drew them closer together. Once time and distance had been changed by the fixed speed of light, motion itself could no longer be described in quite the old way. A moving object gained energy as it moved faster, but near the speed of light, it did not behave like a Newtonian object merely receiving more and more speed. Adding energy made it harder to increase the speed further. The speed of light remained a boundary for objects with mass, and the old separation between mass and energy began to soften. Einstein's famous relation between mass and energy came from this same 1905 period. The equation is often treated as a symbol of sudden power, but its meaning can be approached more calmly. It says that mass corresponds to energy, and the amount of energy associated with even a small mass is very large because the conversion factor involves the speed of light multiplied by itself. The speed of light is already enormous. Squaring it makes the number much larger. This does not mean that ordinary matter is constantly releasing that energy. A book on a table, a cup of water, a stone in a garden, and a person sitting still are not secretly glowing with usable power in any ordinary way. The relation says that mass and energy are connected in the deepest bookkeeping of nature. To turn mass into other forms of energy requires physical processes that allow such a change. The possibility is real, but it is not casually available. A simple way to begin is with heat. When an object is heated, its internal energy increases. In a fully precise relativistic description, that increase in energy also corresponds to a tiny increase in mass. The change is far too small to notice with ordinary scales, but conceptually it matters. Energy does not merely visit matter as an outside property. Energy contributes to the total mass of a system. A hot object has slightly more mass than the same object when cold because its internal energy is greater. The same idea applies more visibly inside atoms. An atomic nucleus is held together by forces much stronger than everyday chemical bonds. Protons repel one another electrically because they have the same positive charge, yet inside many nuclei they remain bound with neutrons. The mass of a bound nucleus is not always equal to the simple sum of the masses of its separated parts. Some of the mass appears as binding energy, the energy associated with holding the nucleus together. This mass difference is small in ordinary human terms, but nuclear processes make it measurable. When certain nuclei split, or when light nuclei combine, the total mass of the products can be slightly less than the total mass before the reaction. The missing mass has not vanished. It has been released as energy carried by motion, radiation, and other products of the process. Relativity gives the conversion rule that tells how much energy corresponds to the lost mass. Lise Meitner and Otto Frisch gave one of the most important interpretations of this kind of process in 1938 and 1939. After experiments by Otto Hahn and Fritz Strassmann showed that uranium bombardment could produce barium, Meitner and Frisch understood that the uranium nucleus had split. They used the language of fission, borrowing the word from biology, where a cell can divide. Their interpretation connected the splitting of the nucleus with the release of energy predicted by the mass-energy relation. The story should be handled without turning it into a tale of spectacle. The scientific point is that a small difference in nuclear mass can correspond to a large release of energy. In nuclear fission, a heavy nucleus separates into lighter fragments, and the final arrangement is more tightly bound in a way that leaves energy available to be carried away. The numbers are not magic. They are the result of mass, energy, and binding being part of one account. Inside this account, mass is not merely stuff, and energy is not merely activity. A system's mass includes the energy inside it, the motion of its particles, the binding of its parts, the fields involved in holding it together, and the radiation it contains, all contribute to the system's total energy and therefore to its mass. A box filled with light, if perfectly mirrored and measured as a whole, would have more mass than the same box without that trapped light. The light has energy, and that energy contributes to the box's inertia. Inertia is the resistance an object has to changes in motion. The more mass something has, the harder it is to accelerate. Relativity connects inertia with energy more closely than older physics did. If energy is added to a system, the system's resistance to acceleration increases by the corresponding amount. This is not usually noticeable in a heated stone or a charged battery, but in high-energy physics, it becomes part of ordinary calculation. Particle accelerators must account for energy and mass together. A fast-moving particle gives another doorway into the idea. As energy is added to a particle with mass, its speed increases at first. But as it approaches the speed of light, more and more energy goes into increasing its total energy rather than simply raising its speed in the old Newtonian way. The particle can move very close to light speed, but it cannot reach light speed. The closer it gets, the more difficult further acceleration becomes. The boundary is not a wall in space. It is built into the relation between energy, mass, and motion. This is why the speed of light becomes a cosmic speed limit for ordinary matter. Anything with rest mass would require an unbounded amount of energy to be accelerated all the way to light speed. Light itself can travel at that speed because photons have no rest mass. They are not slow objects that have been pushed faster and faster. They belong to the structure of electromagnetic radiation and move at light speed in vacuum by their nature. The distinction helps remove a common confusion. Relativity does not say that mass simply becomes larger in a crude mechanical sense as an object moves faster, as if it were swelling or gathering material. Older language sometimes spoke of relativistic mass, but modern explanations usually prefer to keep rest mass fixed and describe the increase in total energy and momentum. The object's own rest mass remains the same. Its energy in another frame depends on its motion. For someone learning slowly, the practical lesson is enough. Mass and energy are not isolated categories. Energy has inertia. Bound systems can have masses that reflect the energy holding them together. Nuclear reactions can release energy when the final mass is lower than the initial mass. The famous relation tells how large that energy difference is. It is a rule of accounting, but the account belongs to nature itself. The relation also showed that special relativity was not only about clocks and rulers. Time dilation and length contraction changed measurement. Mass-energy equivalence changed the understanding of matter. The theory had reached from moving observers into the internal structure of physical systems. It showed that the fixed speed of light shaped not only what different observers measured, but also how energy and mass belonged to the same physical order. This did not make all matter unstable, and it did not turn every object into a waiting explosion. Most mass in daily life remains locked inside stable forms. Chemical processes rearrange electrons and bonds, releasing energies far smaller than nuclear changes. A candle burns because atoms share and exchange electrons in new arrangements, not because large amounts of nuclear mass are converted. Relativity is present in the background, but ordinary chemistry usually lives at a different scale. Nuclear physics made the connection impossible to ignore. In stars, light nuclei combine under immense pressure and temperature, releasing energy through fusion. In certain heavy nuclei, fission can release energy through splitting. In both cases, the final mass-energy balance tells the story. The energy that later appears as heat, light, or motion can be traced to a difference in the mass and binding of the particles involved. Even then, relativity should not be reduced to its most dramatic applications. The mass-energy relation is broader and quieter than the history often attached to it. It belongs to particles in accelerators, nuclei in stars, atoms in laboratories, and every physical system whose energy can be counted. It is one of the reasons modern physics treats matter less as solid substance and more as organized energy in stable form. Special relativity had begun with light and motion, with observers comparing clocks and rulers. Now it had reached the substance of matter itself. Time could differ between moving clocks. Length could differ between moving frames. Energy and mass could no longer be kept apart in the older way. The theory was still incomplete, however, because gravity remained outside it. Newton's force still acted across space, while special relativity had made the transmission of influence and the structure of measurement more delicate. Einstein's next difficulty was therefore waiting in the oldest falling motion of all. Chapter 7. 10 Years Toward Gravity. Gravity was the great unfinished problem after special relativity. Einstein had changed the meaning of time, distance, motion, and energy. But Newton's gravity still stood in the older world. It treated gravity as a force between masses, acting across space according to a law that worked with great accuracy. A planet could pull on the sun could pull on a planet, Earth could pull on a falling stone, and the calculations gave results that matched ordinary experience and astronomical measurement. There was no easy reason to discard Newton's theory. It had guided astronomy for more than 2 centuries. It explained tides, projectiles, falling bodies, planetary orbits, and the motion of moons. Even small irregularities could often be handled by finding another mass nearby or improving the calculation. Newtonian gravity was one of science's most successful descriptions of nature, and any new theory had to preserve that success where Newton's theory already worked. Special relativity created pressure because it changed how influence could travel. If nothing with information can move faster than light, then gravity could not be treated casually as an instant connection across empty space. Newton's mathematics allowed one mass to affect another without delay. That had been acceptable in the older framework, where absolute time ran everywhere at once. After special relativity, the idea of instantaneous action sat uneasily beside the fixed speed of light. Einstein began to think about gravity again in 1907. Later, he called the key insight one of the happiest thoughts of his life, though the idea itself can be stated plainly. A person falling freely does not feel their own weight in the usual way. If an elevator cable were cut, and the elevator, person, and everything inside fell together, objects inside would appear to float. Locally, for a short time and in a small region, falling under gravity could feel like the absence of gravity. The same thought can be turned around. A person standing in a closed elevator in empty space, far from planets and stars, would feel pressure under their feet if the elevator accelerated upward. A dropped object would seem to fall toward the floor. Without looking outside, the person might not be able to tell whether the floor pressed upward because the elevator was accelerating, or because the elevator was resting on the surface of a planet. Gravity and acceleration could imitate one another. This became the equivalence principle. Its simplest form says that the effects of gravity and acceleration are locally equivalent. The word locally matters. Across a large region, gravity can vary from place to place, and tidal effects can reveal the difference between a gravitational field and simple acceleration. But inside a small enough region, and for a short enough measurement, the two can be treated as the same. A falling laboratory becomes, for a moment, a place where gravity seems to have disappeared. The idea changed the direction of the problem. Instead of treating gravity as an ordinary force added onto special relativity, Einstein began to ask whether gravity was connected to the structure of space and time themselves. If acceleration affected how clocks and light were measured, and if gravity was locally equivalent to acceleration, then gravity too should affect clocks and light. The path from that thought to a complete theory was long, because the physical idea needed a mathematical language strong enough to carry it. A simple clock already shows the direction. In an accelerating rocket, light sent from the floor toward the ceiling has to reach a ceiling that is moving during the light's travel. Observers inside the rocket describe the light as arriving with a changed frequency. By the equivalence principle, something similar should happen in a gravitational field. Light climbing away from a massive body should lose energy and shift toward lower frequency. A clock deeper in gravity should tick more slowly compared with a clock higher up. This is gravitational time dilation. It differs from the time dilation of special relativity, which comes from relative motion. Here, the difference comes from position in a gravitational field. A clock near a massive object runs more slowly compared with a clock farther away when the clocks are compared carefully. On Earth, the effect is small but real. A clock at sea level ticks very slightly more slowly than a clock on a mountain, because the lower clock is deeper in Earth's gravitational field. Gravity, then, was no longer only about falling objects. It reached into timekeeping. It affected light. It changed the comparison between clocks at different heights. The familiar pull toward the ground became part of a deeper relation between matter, motion, and the measurement of spacetime. Einstein was not adding decoration to Newton's gravity. He was trying to rebuild gravity so that it could live inside a universe where light speed, time, and measurement had already been changed. The difficulty was mathematical. Special relativity could be written in the language of inertial frames, observers moving steadily without acceleration. Gravity was different because it involved acceleration, changing motion, and fields that varied from place to place. A single flat structure of spacetime was not enough if gravity itself changed the way clocks and rulers compared across regions. Einstein needed geometry, but not the familiar geometry of flat surfaces and straight lines. Marcel Grossmann, a mathematician and friend from Einstein's student years, helped point him toward the needed tools. The geometry developed by Bernhard Riemann allowed curved spaces to be described mathematically. In such geometry, the rules of distance and direction can vary from point to point. A line can be straight in the sense of following the most natural path available, even when the larger surface or space is curved. This gave Einstein a possible language for gravity. The work was slow and difficult. Between the 1907 insight and the completed field equations in 1915, Einstein moved through false starts, partial formulations, corrections, and mathematical struggle. He had to preserve the success of Newton's theory in ordinary conditions while extending it into a more general framework. He also had to make the theory agree with special relativity, where gravity could be ignored. A new theory of gravity could not merely be imaginative. It had to reduce to the older, successful theories in the places where those theories had already earned trust. Mercury's orbit became one of the important tests waiting in the background. The planet's path around the Sun had a small irregularity in the motion of its perihelion, the point where it comes closest to the Sun. Newtonian physics explained almost all of this motion by accounting for the gravitational influence of other planets, but a small leftover remained. It was not large. It was measured in arcseconds per century, yet it was persistent enough to matter. Einstein's developing theory had to explain such leftovers without ruining everything Newton had explained. That is a demanding kind of progress. A theory that changes too little solves nothing. A theory that changes too much loses the old successes. General relativity had to be delicate, carrying Newtonian gravity as an approximation while altering the deeper structure underneath it. In weak gravitational fields and at low speeds, it had to look almost exactly like Newton. Near strong gravity or in precise measurements, it had to show something more. The equivalence principle remained the guiding thread. If gravity and acceleration were locally alike, then gravity could not be just another force in the ordinary sense. Forces usually act within spacetime. Einstein was moving toward a theory in which gravity helped determine the shape of spacetime itself. Objects would still fall. Planets would still orbit, but their motion would be described less as a pull across empty distance and more as movement along natural paths in a curved structure. This does not mean the older word force becomes useless in everyday speech. A person standing on the ground can still say gravity pulls downward. Engineers can still use Newtonian gravity in many calculations. A falling stone can still be described simply. General relativity does not remove the practical language of gravity from daily life. It explains why that language works so well in one region and why a different description is needed when measurement becomes more exact. Einstein reached the final form of general relativity in 1915. The field equations connected matter and energy with the curvature of spacetime. They were mathematically dense, but their physical meaning can be held in simple terms. Matter and energy tell spacetime how to curve. Curved spacetime tells matter and light how to move. That sentence is often used because it carries the basic relation clearly, though the actual mathematics beneath it is far richer. After 10 years, gravity had changed from a force acting inside space into a feature of spacetime's geometry. The change did not erase falling apples or orbiting moons. It placed them in a larger description: a clock near Earth, a ray of light passing close to the Sun, a planet moving around its star, and a body falling freely all became parts of one geometry. The path toward that geometry began with a falling elevator and the recognition that weight itself could be more subtle than it seemed. The next step is to make that geometry easier to feel without turning it into a misleading picture. Spacetime is not a rubber sheet floating inside a larger room, and gravity is not simply a dent in a visible surface. Yet the idea of curvature can still be approached slowly. If time and space are joined, and if gravity changes how clocks, light, and paths behave, then space-time itself must have structure under weight. Chapter 8. Space-time under weight. Space-time is one of those words that can make a simple idea feel difficult before the explanation has even begun. It sounds as if physics has taken two familiar things, space and time, and fused them into something abstract. Yet the reason for joining them is not decorative. Special relativity had already shown that observers moving differently do not divide time and distance in the same way. One observer's time measurement can become partly another observer's distance measurement, and one observer's distance measurement can depend on how clocks are synchronized. Before relativity, Space and time could be imagined as separate backgrounds. Space was where things were located. Time was when things happened. A body moved through space as time passed, and those two pieces seemed cleanly distinct. After special relativity, that separation became less secure. Time and space still mattered, but they were no longer independent containers. They behaved more like two aspects of a single structure, divided differently by different observers. Hermann Minkowski gave this idea a powerful mathematical form in 1908. He had once been one of Einstein's teachers, and he recognized that special relativity could be understood through a four-dimensional structure. 3 dimensions described space: length, width, and height. The 4th dimension described time, though not exactly like the others. Events, rather than objects alone, became the basic points of the structure. An event is something that happens at a place and at a time. This helps make the idea less mysterious. A meeting, a flash of light, a clock tick, a particle decay, and a planet reaching a certain point in its orbit can all be treated as events. To describe an event fully, it is not enough to say where it happened. The time must also be given. Likewise, it is not enough to say when it happened if the place is unknown. Spacetime is the combined record in which events have both location and timing. Special relativity described spacetime as flat. Flat does not mean visually flat, like a floor or a sheet of paper. It means that, without gravity, the rules of geometry behave in a certain simple way. Light follows straight paths. Objects with no forces acting on them move steadily. Clocks and rulers differ between moving observers, but those differences are organized by one consistent structure. Special relativity is already strange compared with Newton, but its spacetime is still mathematically clean. Gravity made that clean structure insufficient. If gravity affects clocks, light, and motion, then spacetime cannot remain the same everywhere. A clock near a massive body runs differently from a clock farther away. A beam of light passing near the sun follows a path that appears bent. A planet does not move in a perfect Newtonian ellipse when measurement becomes precise enough. These are not separate tricks. They point toward a shared change in the geometry through which matter and light move. Riemannian geometry gave the needed language. Bernhard Riemann had developed a way to think about spaces whose geometry could vary from place to place. In ordinary flat geometry, the rules learned in school work smoothly. Parallel lines remain parallel. The angles of a triangle add to the familiar amount. The shortest path between 2 points is a straight line. On a curved surface, those rules can change. A triangle drawn on Earth's surface can have angle sums different from a flat triangle because the surface itself is curved. That surface example is useful only if it is handled carefully. Spacetime is not merely a 2-dimensional surface bent into a higher room. It is 4-dimensional, and its curvature is not something the eye can step outside and inspect. The surface of Earth helps only by showing that geometry can have internal rules that differ from flat expectations. Creatures living on a curved surface could detect curvature by measuring distances, angles, and paths, even if they could not look at the surface from outside. Marcel Grossmann helped Einstein find his way into this mathematics. Einstein had the physical insight that gravity and acceleration were linked, and that gravity must affect clocks and light. Grossmann understood the mathematical tools that could express curved geometry. Their collaboration helped turn a guiding idea into a theory capable of calculation. In general relativity, mass and energy are connected with the curvature of spacetime. A massive body does not merely sit inside an unaffected stage. Its presence changes the geometric relations around it. Clocks, rulers, and paths are part of that altered structure. A planet orbiting the sun is not being pulled in the old image of an invisible rope reaching across emptiness. It is following a natural path through space-time shaped by the sun's mass and energy. The common rubber sheet picture tries to make this visible. A heavy ball placed on a stretched sheet creates a dip, and smaller balls roll around it. The picture has some value because it suggests that motion can follow from curvature rather than from a direct pull, but it also misleads. The sheet is two-dimensional. It uses Earth's gravity to make the smaller balls roll, and it shows space curving without showing time properly. Relativity is deeper than that image. The curvature includes time, and time is crucial to how gravity works. A better slow thought is to return to clocks. Near a massive body, time runs more slowly than it does farther away. This difference in clock rates is not added after the geometry is built. It is part of the geometry. The paths that objects follow through spacetime depend on how time and space are shaped together. In weak gravity, such as near Earth, the effect is small. Near a very dense mass, the change becomes stronger, and the difference between clocks can become large. Light also follows the geometry. Since light always travels locally at light speed, it does not slow down in the ordinary sense as it passes near a massive body. But the path available to it is shaped by curved spacetime. To a distant observer, the light's route can appear bent. This is why gravity can affect light without treating light as a normal object with rest mass. The light is not being grabbed like a stone. It is following the straightest possible path through a geometry that is not flat. The phrase "straightest possible path" needs a little patience. On a flat map, the shortest route between 2 points looks like a straight line. On Earth's surface, long-distance aircraft routes can look curved on a flat map, even when they follow efficient paths across the globe. The geometry decides what counts as the natural path. In curved spacetime, planets, falling objects, and beams of light follow paths called geodesics. They are the natural lines of motion inside the geometry available to them. A falling object illustrates this without needing cosmic scale. When a stone is released near Earth, Newton's description says gravity pulls it downward. General relativity says the stone follows a path through curved spacetime, while the ground prevents everything resting on it from following its own free-fall path. A person standing on the ground feels weight because the ground pushes upward, preventing free fall. A person falling freely for a short time feels weightless because they are following the natural path gravity gives. This returns to Einstein's elevator. Inside a freely falling elevator, objects float together because they share the same natural motion through spacetime. Gravity has not disappeared from the larger situation. Earth is still there, and the path is still shaped by Earth's mass. But locally, the falling frame behaves as if gravity has been transformed away. That local removal is one of the signs that gravity is not quite like ordinary forces. It can be made to vanish in a small falling laboratory because it is bound to the frame and geometry of motion. A magnetic force cannot be removed in the same way for every object by simply falling. Electric and magnetic forces depend on charge and act differently on different kinds of particles. Gravity, by contrast, affects all freely falling bodies in the same way, ignoring their composition under ordinary conditions. This universality is one reason geometry fits gravity so naturally. If every object follows the same kind of free-fall path, the path seems to belong to the structure of spacetime rather than to a special property of the object. Einstein completed the field equations of general relativity in 1915. They connected the distribution of mass and energy with the curvature of spacetime. The equations are not spoken here because their symbolic form is not needed for the slow meaning. Their role was to make the relationship precise. Given matter and energy, the equations describe how spacetime curves. Given that curvature, they describe how matter and light move. This is why general relativity is both simple in outline and difficult in full detail. The simple outline says gravity is geometry. The full theory must calculate exactly how geometry changes around stars, planets, galaxies, and dense remnants. It must recover Newton's predictions, where gravity is weak and speeds are low. It must also explain small deviations, such as Mercury's orbit, and new effects, such as light bending near the Sun. The theory's strength lies in doing both. Spacetime under weight, then, is not a poetic phrase. It is the central change in the theory of gravity. Mass and energy alter the measurements of time and distance around them. Objects move along natural paths in that altered structure. Light follows those paths as well. The familiar pull of gravity becomes the everyday surface of a deeper geometry, one that remains nearly hidden near Earth but becomes measurable through clocks, orbits, and beams of light. Once gravity has become geometry, a new prediction follows with unusual clarity. If light passes near a massive body, its path should shift. The Sun should bend starlight by a small but measurable amount. Mercury's orbit should carry a leftover correction that Newton's theory could not fully explain. General relativity now had to meet observation because a theory of curved spacetime could not remain only an elegant way of speaking. It had to show itself in the path of light. Chapter 9. How gravity bends light. Light does not have to be heavy to be affected by gravity. That is one of the first confusions general relativity removes. In Newton's older picture, gravity was easiest to imagine as a force pulling on masses. A stone falls because Earth pulls on the stone. The Moon orbits because Earth's gravity keeps changing the Moon's path. The Sun holds planets near it because its mass dominates the solar system. Light, having no ordinary rest mass, seems at first as though it should pass through such a system untouched. General relativity changes the question. Gravity is not treated as a simple pull acting inside an unchanged space. It is the shape of spacetime itself, and light moves through that shape. Locally, light still travels at light speed. A beam passing near the Sun does not slow down in the simple way a ball slows while climbing against gravity. It follows the straightest path available inside curved spacetime, and because the geometry near the Sun is curved, that path appears bent when seen from far away. The bend is small near the Sun, but small does not mean unimportant. Light from a distant star passing close to the Sun should arrive at Earth from a slightly shifted direction. The star would appear to sit in a position just a little different from where it appears when the Sun is not near its line of sight. No one needed to touch the star. No one needed to travel to the Sun. The test required measuring the apparent positions of stars with enough care to see whether sunlight's path had been altered by gravity. Einstein had considered the bending of light before his final theory was complete. In an earlier calculation, using the equivalence principle but not the full curved spacetime theory, he obtained only part of the final answer. General relativity doubled the predicted deflection. That mattered because the difference between the older and newer values could, in principle, be tested. A theory becomes stronger when it gives nature a chance to disagree with it. The Sun offered the most practical nearby test. Its mass is large enough to bend light measurably, and distant stars provide background points whose apparent positions can be compared. But the Sun also creates the main difficulty. Its brightness hides the stars around it. On an ordinary day, the stars near the Sun's apparent position are still there, but the sky is flooded with sunlight. The measurement becomes possible only during a total solar eclipse, when the Moon covers the Sun's bright disk and the nearby stars briefly appear. A total eclipse is a narrow permission. The Moon's shadow falls across only certain parts of Earth. Weather may interfere. Instruments must already be in place. Photographic plates must capture stars whose positions can later be compared with reference plates taken when the sun is elsewhere. The whole test depends on a short interval during which the sky allows a measurement that is normally hidden. It is a patient kind of experiment, built around timing, geography, and small angular shifts. Another early test came from Mercury. Mercury moves closest to the Sun, so it travels through stronger solar gravity than the other planets do. Its orbit is not a fixed ellipse. The point of closest approach to the Sun, called the perihelion, slowly shifts. Newtonian physics explained almost all of this shift by including the gravitational influence of the other planets. A small leftover remained, about 43 arcseconds per century. That is an extremely small angle, but it had been measured and resisted full Newtonian explanation. General relativity accounted for that leftover. In the curved spacetime near the Sun, Mercury's orbit follows a path slightly different from the one Newtonian gravity predicts. The correction is tiny, but it lands exactly where the old theory had a persistent gap. For Einstein, this was one of the first strong signs that the new theory had reached something real. It did not merely speak differently about gravity. It explained a known measurement that had been waiting for a better framework. The Mercury result is useful because it shows the character of general relativity. The theory does not replace ordinary astronomy with fantasy. It changes the calculation where gravity is strong enough or measurement is precise enough for the difference to matter. For most planets, Newton's theory works very well. For Mercury, close to the Sun, a small correction appears. General relativity earns trust not by making everything unfamiliar, but by explaining exactly where the familiar theory begins to fall short. Light bending belongs to the same pattern. A beam of light passing near a massive body does not veer wildly away in everyday cases. Near the Sun, the predicted deflection for starlight grazing the solar edge is about 1.75 arcseconds. An arcsecond is 1/60th of an arc-minute, which is 1/60th of a degree. The number is small enough to make the test difficult and precise enough to make the prediction serious. The evidence would have to come from careful comparison, not from spectacle. A simple way to hold the idea is to think of a map where the route is straight according to the land itself, but curved according to the flat paper. Long paths on Earth can appear curved when drawn on a flat projection, even when they are natural paths across the globe. Light near the Sun is not choosing to curve in a conscious way, nor is it being pulled aside like a thrown ball. It follows the geometry available to it. A distant observer, comparing that path with what flat space would have given, calls the result bending. This is why the phrase "gravity bends light" is both useful and incomplete. It is useful because the apparent position of the light source changes. It is incomplete because the deeper claim is about space-time geometry. Light follows null paths through space-time, paths suited to something moving at light speed. When the geometry is curved by mass and energy, those paths are altered. The visible bending is the observational surface of the deeper structure. Later astronomy turned this effect into a tool. Gravitational lensing occurs when a massive object lies between Earth and a more distant source of light. The foreground mass curves spacetime, and light from the background object can be bent into arcs, multiple images, or magnified forms. Galaxies and clusters of galaxies can act as natural lenses. The same principle that shifts starlight near the Sun can, on larger scales, help astronomers study distant galaxies and map invisible mass. That later use should not make the original idea harder than it is. Gravity changes the path that light takes. The stronger and larger the gravitational field, the more noticeable the bending can become. Near the Sun, the effect is small and difficult to measure. Near galaxies and clusters, it can become large enough to shape images across astronomical photographs. In both cases, the principle remains the same. Light follows the geometry of spacetime. Mercury's orbit and light bending gave general relativity two different kinds of evidence. Mercury involved the path of a planet with mass. Light bending involved the path of something without rest mass. Both pointed toward the same theory. Gravity was not only pulling material bodies in the older sense, it was shaping the conditions under which motion itself occurred. Planets, clocks, and beams of light all became witnesses to the same geometry. There is a calm precision in these tests. Nothing in them depends on making gravity sound mysterious. Mercury's orbit has a small excess precession. Starlight near the Sun has a small angular deflection. Clocks at different heights tick at slightly different rates. Each effect is narrow enough to be measured, and together they form a pattern. The theory survives because the pattern keeps appearing where the mathematics says it should. Einstein's calculation of Mercury's orbit came before the eclipse result made him famous to the wider public. For the scientific theory itself, Mercury already mattered deeply. It was a known anomaly, a specific mismatch between Newtonian prediction and observation. General relativity did not need to invent a new problem to solve. It walked into an old one and supplied the missing correction. The planet nearest the Sun became one of the earliest places where curved spacetime left a numerical signature. The bending of light, however, had public force because it could be connected with an event in the sky. A solar eclipse gives a date, a location, and a brief interval in which the measurement can be attempted. It allows a difficult idea to attach itself to photographs of stars. General relativity would not become true because of public attention, but public attention would gather around the eclipse because the test seemed to place Einstein's theory under the open sky. The next stage, then, was not another thought experiment. It was an expedition. Astronomers would have to carry instruments to places where the eclipse could be observed, photograph stars close to the hidden sun, and compare their positions with the predicted deflection. The theory of curved spacetime had reached the point where a tiny displacement on a photographic plate could speak for or against it. Chapter 10. The eclipse that tested the theory. A scientific theory can be beautiful on paper and still need the discipline of measurement. General relativity had explained Mercury's small orbital irregularity and had given a new account of gravity, but the theory also made a prediction that could be tested with light. Starlight passing near the Sun should appear slightly displaced because the Sun's mass curves spacetime around it. The predicted shift was very small, but it was not vague. It had a number attached to it. The difficulty was practical. Stars near the Sun are normally hidden by daylight. Their light still reaches the region of the sky around the Sun, but the Sun's brightness overwhelms them. The total solar eclipse briefly changes that condition. When the Moon covers the Sun's bright face, stars close to the Sun's apparent position can become visible enough to photograph. For a few minutes, the sky permits a measurement that ordinary daylight prevents. The eclipse of May 29, 1919, became the test. The path of totality crossed regions where astronomers could set up instruments and photograph the star field near the covered Sun. Two observing sites became central: Sobral in Brazil and the island of Principe off the west coast of Africa. The expeditions were organized under difficult conditions after the First World War, with scientific cooperation carrying a weight that was not only technical. Arthur Eddington, a British astronomer and Quaker, became the figure most closely associated with the Principe observations. Eddington already knew Einstein's theory before the eclipse. He had helped explain and promote general relativity in the English-speaking scientific world at a time when wartime divisions had made communication between German and British scientists more difficult. His interest in the eclipse test was scientific, but it also belonged to a damaged international moment. A German-born theory, tested by British-led expeditions just after the war, carried a human context around the measurement. The photographic plates still had to decide the matter. The method was conceptually simple. Photographs of stars near the sun would be taken during totality. Other photographs of the same star field would be taken when the sun was not in that part of the sky. By comparing the positions, astronomers could see whether the stars appeared shifted during the eclipse. If general relativity was correct, starlight passing close to the sun should be deflected by about 1.75 arcseconds at the solar limb. If the older Newtonian style estimate was used, the deflection would be about half that value. An arcsecond is a very small angle. 1 degree is divided into 60 arc minutes, and each arc minute is divided into 60 arc seconds. The entire predicted shift was far below what the unaided eye could detect. It had to be inferred from careful measurements of star images on photographic plates. Dust, weather, instrument focus, temperature, exposure length, and the quality of the comparison plates all mattered. The test was famous later, but at the time it was also fragile in the ordinary ways field astronomy can be fragile. At Sobral, the observers had better weather. Several photographic plates were taken, though not all instruments performed equally well. One telescope produced images that were less reliable because of focus problems, likely connected to the sun's heat affecting the instrument. Another set of images, taken with a smaller instrument, gave results closer to Einstein's prediction. The data had to be sorted carefully, and the strongest conclusion came from judging which plates and instruments deserved the most weight. At Principe, Eddington faced clouds. The eclipse was not a long, uninterrupted window of clear sky. The useful photographs were limited. Still, some star images were captured, enough to allow measurements, though with uncertainty. The romantic version of the story sometimes makes the result feel immediate, as if the clouds parted and truth appeared cleanly on glass. The actual work was more patient. It involved partial data, imperfect conditions, and later analysis. When the results were announced in November 1919, they were presented as supporting Einstein's prediction. The Royal Society and the Royal Astronomical Society heard the findings, and newspapers soon turned Einstein into an international public figure. Headlines simplified what had happened. The public story became one of a new theory overturning Newton. The scientific story was more careful. Newton's theory still worked extremely well in weak gravity and ordinary conditions. General relativity had supplied a more exact description, where the older theory missed small effects. The eclipse did not make relativity true by itself. No single experiment, especially one with difficult data, carries an entire theory alone. But the 1919 observations mattered because they addressed a clear prediction. They showed that gravity affected light in a way consistent with the new theory. Later measurements, made with better instruments and different methods, would test light deflection and gravitational lensing with far greater precision. The eclipse became the doorway through which a wider scientific and public world entered the theory. Eddington's role has sometimes been debated because he was sympathetic to Einstein's theory, and because the 1919 data were not as clean as later retellings suggested. That caution is useful. It keeps the story from becoming myth, yet it does not erase the scientific importance of the expedition. The observations were part of a larger accumulation of evidence, and general relativity would continue to survive tests that were far more exact than the eclipse plates. The early measurement was imperfect, but it pointed in the direction the theory had predicted. There is a useful distinction between fame and confirmation. Einstein became famous very quickly after the eclipse announcement. Confirmation came more slowly through repeated tests, refined measurements, and the theory's success across different phenomena: Mercury's orbit, gravitational redshift, light deflection, time dilation, gravitational waves, and modern satellite corrections all belong to that longer story. Public fame can arrive in a day. Scientific trust is built across decades. The eclipse test also helped change how gravity was pictured. If light's apparent path shifted near the sun, then gravity was not merely a force acting on heavy bodies. It affected the route taken by light itself. Since light carried no rest mass, the result made strongest sense inside the curved spacetime picture. A star's apparent position on a photographic plate had become a sign of geometry near the sun. This was a quiet kind of evidence. The star did not move. The sun did not announce curvature. The photographic plate showed small points of light, and the measurement lay in their slight displacement. A person looking at the plate without context might see only dots. Physics turned those dots into a comparison between two pictures of gravity. One picture treated space and time as a stage where forces acted. The other treated space-time as part of the gravitational field itself. By the early 20th century, astronomy had become skilled at extracting meaning from tiny differences. A shift in a spectral line could reveal motion. A faint blur could turn out to be a galaxy. A small irregularity in an orbit could suggest an unseen planet or a missing correction in the law. Relativity entered that tradition. It did not ask the eye to witness curved space-time directly. It asked instruments to record the consequences. For Einstein, the eclipse result brought a level of attention that few theoretical physicists had ever experienced. He had already done the central work. The theory had been completed in 1915, and Mercury's perihelion had already given him a powerful internal confirmation. But after 1919, his name moved outside scientific circles. Relativity became a public symbol of modern thought, often admired before it was understood and sometimes rejected for the same reason. That public confusion has never fully disappeared. Relativity still carries an aura of difficulty. People repeat phrases about time slowing and space bending without always knowing what problem those phrases solved. The eclipse story helps because it returns the theory to a concrete test. Light from stars passed near the sun. Photographic plates recorded where that light seemed to come from. The positions shifted by a tiny amount. The shift agreed more closely with curved spacetime than with the older expectation. A theory of gravity had met light, and light had answered through measurement. The answer was not loud. It came as an angle too small for human sight, preserved on plates exposed during a few minutes of darkness under an eclipsed sun. From there, relativity moved further outward. If spacetime could curve enough to bend starlight near the sun, then more extreme masses could shape paths far more severely, and the same equations would begin to describe places where escape itself becomes impossible. Chapter 11. Black holes and the edge of the map. Black holes enter relativity as a consequence before they enter the imagination. They are often pictured as cosmic traps, dark mouths, or impossible holes in space. But the theory reaches them through a quieter path. General relativity says that mass and energy shape space-time. If enough mass is gathered into a small enough region, the curvature becomes so strong that the paths available to matter and light change completely. The result is not a surface made of material, and not an object in the ordinary sense. It is a region of space-time with a boundary beyond which escape is no longer possible. The first mathematical doorway opened almost immediately after Einstein completed general relativity. In 1916, Karl Schwarzschild found an exact solution to Einstein's field equations for the gravitational field outside a spherical, non-rotating mass. Schwarzschild was serving in the German army during the First World War when he did this work. The circumstances were harsh, and the calculation itself was demanding. But the result was clean enough to become one of the central solutions in general relativity. It described how space-time behaves around an idealized spherical mass. Inside that solution appeared a strange radius. If all the mass of an object were compressed inside this radius, then the escape speed at the boundary would equal the speed of light. In older language, one might say that not even light could escape. In general relativity, the meaning is more exact. Once a path crosses that boundary inward, all future directed paths lead farther inward. Escape is not difficult in the way climbing a steep hill is difficult. It is unavailable because the geometry points every possible future deeper inside. That boundary is now called the event horizon. The name is careful. It is a horizon because it marks the limit beyond which events cannot send information back to the outside universe. It is not a wall. A traveler crossing a large black hole's horizon would not necessarily strike a surface there. Locally, the passage could be uneventful at the crossing itself, depending on the black hole's size. The boundary matters because of what it does to paths, signals, and communication. A horizon can be approached by thinking about escape. On Earth, a rocket needs enough speed to leave the planet's gravitational hold. A more massive or more compact object requires a higher escape speed. If an object becomes compact enough, the escape speed at a certain boundary reaches light speed. Since nothing carrying information can exceed light speed, nothing from inside that boundary can return outward. General relativity expresses this more deeply than escape speed language does, but the simple picture gives a first handhold. Schwarzschild's solution did not immediately create the modern idea of an astrophysical black hole. For many years, such objects were treated cautiously. Some physicists wondered whether the strange features of the solution were artifacts of the coordinates used in the mathematics. Others doubted that nature would ever compress matter enough to make such a region real. The equations had opened a possibility, but possibility is not the same as an observed object. Physics had to learn whether stars could actually reach that state. The path toward physical black holes passed through the lives of stars. A star holds itself in balance through pressure and gravity. Gravity draws matter inward. Pressure from heat, radiation, and later quantum effects can resist collapse. When a star exhausts the nuclear fuel that supports it, its future depends heavily on its mass. Some stars become white dwarfs. More massive stars can become neutron stars. If the remaining core is massive enough, no known pressure can halt the inward collapse completely. Subrahmanyan Chandrasekhar helped clarify one part of this story in the early 20th century. He calculated that white dwarfs have a mass limit, now called the Chandrasekhar limit. Above that limit, electron degeneracy pressure cannot support the star against gravity. Later work on neutron stars and gravitational collapse showed that other forms of pressure also have limits. The life of a massive star could therefore lead toward an object compact enough for the Schwarzschild radius to become physically relevant. The word collapse can make the process sound sudden in a way that distracts from the physics. What matters is the final condition. Matter becomes concentrated into a region where the curvature of spacetime is extreme. Outside, the black hole can be described by mass, rotation, and electric charge. Though astrophysical black holes are usually discussed mainly through mass and spin, the details of the original star become hidden from the outside once the horizon forms. What remains visible is the gravitational field. Rotation makes real black holes more complex than Schwarzschild's original idealized solution. Roy Kerr found a solution in 1963 describing a rotating black hole. Since stars rotate, and since collapsing matter carries angular momentum, rotating black holes are expected in nature. Around such objects, spacetime itself is dragged by the rotation, a phenomenon known as frame dragging. The simple spherical picture remains useful for first understanding, but the real universe rarely supplies perfect stillness. A black hole is dark because light from inside the event horizon cannot reach the outside. Yet black holes can be found because their surroundings are often bright. Gas falling toward a black hole can heat to very high temperatures and emit intense radiation before crossing the horizon. Stars orbiting an unseen compact mass can reveal its presence through their motion. X-ray sources, galactic centers, gravitational lensing, and later gravitational waves all gave astronomers ways to infer black holes without needing light to come from inside them. Cygnus X1 became one of the early strong black hole candidates. It is an X-ray source in the constellation Cygnus, associated with a massive unseen companion drawing material from a visible star. The X-rays come from hot material near the compact object. The mass inferred for the unseen companion made a neutron star explanation difficult, leaving a black hole as the stronger interpretation. This was not proof by image, it was proof by motion, radiation, and mass. At the center of the Milky Way, stars orbit an unseen compact object called Sagittarius, a star. Careful observations over years showed stars tracing tight paths around a mass of about 4 million times the mass of the Sun. contained in a very small region. The motions were measured by teams using large telescopes and infrared observations because dust hides the galactic center in visible light. The result became one of the clearest cases that supermassive black holes occupy galactic centers. The Event Horizon Telescope added another kind of evidence in 2019. It combined radio observatories across Earth to create an Earth-sized virtual telescope using a method called Very Long Baseline Interferometry. The first released image showed the shadow of the black hole in the galaxy M87, surrounded by emission from hot material nearby. The image did not show the event horizon directly as a surface. It showed the dark central region shaped by the paths of light near a massive compact object. This image became famous because it gave a visual form to something long described through equations and indirect evidence. Still, its scientific importance rests on measurement rather than appearance. The size of the shadow, the structure of the surrounding emission, and the mass inferred from other observations all had to fit together. The picture was a map of light moving through curved spacetime near a black hole. It was not a photograph of darkness alone. Black holes also sharpen the meaning of time in relativity. To a distant observer, a clock falling toward an event horizon appears to slow as its light becomes increasingly redshifted and faint. The falling clock itself, along its own path, continues to tick normally until local conditions become extreme. This difference is not a contradiction. It follows from comparing time near strong gravity with time far away. General relativity had already shown that gravity affects clocks. Black holes take that effect to its limit. Near a black hole, paths narrow in a way ordinary space does not prepare the mind to picture. Outside the horizon, some paths can still lead away. Closer in, escape requires more careful direction and more energy. At the horizon, every future path that remains physically possible leads inward. The boundary is not marked by a fence, heat, color, or texture. It is marked by the structure of future motion itself. That is why black holes sit at the edge of the map, not because physics has nothing to say about them, but because they carry established theory into extreme conditions. General relativity describes the horizon and the exterior spacetime with great success. It predicts gravitational lensing, orbital motion, time dilation, and the waves produced when black holes merge. But inside, near what the classical theory calls a singularity, the description reaches a limit. Curvature grows beyond what the theory can handle in a complete physical way. A singularity in general relativity is not best understood as a tiny object sitting at the center. It is a sign that the mathematical description has become incomplete. The theory says that paths cannot be extended in the usual way and that quantities describing curvature become unbounded. Many physicists expect that a deeper theory involving quantum gravity is needed there. The singularity is therefore less a place one can sensibly visit in imagination and more a warning that the current map has ended. Black holes connect the strongest successes of relativity with some of its deepest open questions. They have been observed indirectly through stellar motion and radiation. Their mergers have been detected through gravitational waves. Their shadows have been imaged by radio telescopes working together across Earth. At the same time, their interiors, their relation to quantum information, and the final nature of singularities remain unresolved. They are both known objects and frontier problems. For the slow path through relativity, their place is now clear. Special relativity changed time, distance, and energy. General relativity changed gravity into geometry. Black holes are what the geometry allows when enough mass is compressed into a small enough region. They are not exceptions to relativity. They are among its most demanding consequences. Once gravity can shape spacetime so severely, the theory naturally expands from individual stars to the universe as a whole. If mass and energy determine geometry, then the total contents of the universe must matter for the universe's large-scale structure. Einstein's equations could describe a star, a ray of light, and a black hole, but they also raised a larger question. The same theory that curved space near the sun could be asked to describe all of space at once. Chapter 12. the universe that could expand. The universe once seemed easier to imagine as something fixed. Stars had their motions, planets had their orbits, comets came and went, and galaxies, though not yet fully understood, appeared as distant arrangements in a larger stillness. Even when astronomers knew that objects moved, the background itself could be treated as steady. Space was the container, matter moved inside it. The container did not need to grow, shrink, or change its overall shape. General relativity made that older stillness harder to keep. If gravity was the geometry of spacetime, and if matter and energy shaped that geometry, then the universe as a whole could not be treated as a simple empty stage. The total distribution of matter mattered. The large-scale shape of space mattered. Time mattered not only as a clock beside events, but as part of the structure whose behavior the theory was trying to describe. A theory of gravity had become, almost naturally, a theory that could ask what the universe itself was doing. Einstein first tried to apply general relativity to the whole cosmos in 1917. He assumed, as many scientists did, that the universe was static on the largest scale. Not necessarily motionless in every detail, but stable overall. His equations, however, did not comfortably produce that kind of universe without adjustment. Gravity tends to draw matter together, and a static universe filled with matter is not easy to balance. To hold the model steady, Einstein introduced the cosmological constant, a term that could counter gravity's tendency toward collapse. This was not foolish at the time. A static universe seemed reasonable from the evidence then available. The Milky Way was still often treated as if it might be nearly the whole stellar system, and the true nature of many spiral nebulae remained debated. Observational cosmology did not yet have the distance measurements that would later change the picture. Einstein was working at the edge of what the evidence allowed. His mathematics had opened possibilities that astronomy had not yet settled. Alexander Friedmann took a different route in the early 1920s. Working with Einstein's equations, he found solutions in which the universe could expand or contract. Friedmann did not force the cosmos to remain still. He allowed the mathematics to move. His models showed that general relativity could describe a dynamic universe, one whose large-scale distances changed with time. The idea was not immediately absorbed, and Einstein initially resisted Friedmann's work before recognizing the mathematical point. A universe that expands is not quite like an explosion through empty space. That common picture misleads because it imagines galaxies flying outward into a pre-existing emptiness, as fragments might move away from a burst point. Cosmological expansion is subtler. It means that the distances between widely separated galaxies can grow because space itself is changing its scale. The galaxies are not all moving through space from one central location. On the largest scale, space between them is increasing. A simple surface can help if it is not pushed too far. Points drawn on the surface of an inflating balloon grow farther apart as the surface stretches. No point on the surface needs to be the center of expansion for the beings confined to that surface. Every distant point moves away from every other distant point as the surface grows. The actual universe is not the surface of a balloon, and it has 3 spatial dimensions rather than 2. But the example helps separate expansion of space from ordinary motion through space. Georges Lemaitre, a Belgian priest and physicist, also found expanding solutions and connected them more directly to astronomical observation. In 1927, he proposed that the recession of distant nebulae could be understood through an expanding universe. He used available velocity and distance data to suggest that distant objects were moving away at speeds related to their distances. His work did not receive immediate broad attention, partly because of publication language and partly because the astronomical evidence was still developing. Edwin Hubble's observations soon became central to the public and scientific shift. Using the 100-inch Hooker telescope at Mount Wilson, Hubble studied Cepheid variable stars in distant nebulae. Cepheids have a relation between their brightness variation period and their intrinsic luminosity, which allows them to serve as distance indicators. Hubble's work helped show that some spiral nebulae were far beyond the Milky Way. the universe became far larger than many had assumed. Hubble and his collaborators also found a relation between distance and redshift. Light from many distant galaxies was shifted toward longer wavelengths, and the more distant galaxies tended to show larger redshifts. This became one of the foundations of the expanding universe picture. The relation is often called Hubble's law, though the history includes earlier theoretical work by Lemaitre and observational contributions from Vesto Slipher, who had measured many nebular redshifts before the full distance scale was clear. Redshift itself can be explained slowly. Light has wavelength, and wavelength can be stretched. When light from distant galaxies reaches Earth with its spectral lines shifted toward the red end of the spectrum, astronomers can measure that change. In ordinary motion, a similar shift can happen when a source moves away. In cosmology, the deeper interpretation is that the light's wavelength has stretched while traveling through expanding space. The light carries, in its color, a record of the changing scale of the universe. This is where relativity becomes cosmic without becoming vague. General relativity supplies the framework in which space can expand. Observations supply the measurements, showing that distant galaxies tend to recede in a patterned way. The theory and the data meet in the idea that the universe has a history. It was not always the same size. It has changed over time, and that change can be measured through light that has crossed enormous distances. For a listener new to the subject, one confusion is worth softening. If the universe is expanding, it does not mean that every object inside it expands. A person does not grow because cosmic space expands. Earth does not swell. The solar system does not gradually stretch apart because expansion is operating across the room. Gravity, electromagnetic forces, and other local binding effects hold smaller systems together. Expansion becomes important across the vast distances between galaxy clusters, where the large-scale geometry dominates. The expanding universe also changed the meaning of cosmic time. If galaxies are farther apart now than they were in the past, then one can reason backward toward a denser, hotter, earlier state. Lemaitre would later speak of a primeval atom, an early idea pointing toward what became Big Bang cosmology. The modern Big Bang picture is not an explosion in space. It is the early hot, dense state of space itself, followed by expansion and cooling. General relativity gave the language in which that history could be described. Einstein's cosmological constant did not disappear forever. After the expanding universe became accepted, Einstein reportedly regarded its earlier use to hold the universe static as a mistake, though the exact famous phrasing attached to that regret is historically uncertain. Later, the cosmological constant returned in another form. Observations of distant supernovae in the late 20th century indicated that cosmic expansion is accelerating, and a cosmological constant or something like it became part of the standard model of cosmology. An idea first used to preserve stillness returned as part of a changing universe. This return is a useful reminder that scientific concepts can outlive their first purpose. The same mathematical term can be introduced for one reason, rejected or set aside, and then reappear under different evidence. In the current cosmological model, dark energy is the name given to whatever drives the observed accelerated expansion, with the cosmological constant as the simplest possibility. The details remain an active research subject, but the broad point is clear enough. General relativity still frames how cosmologists describe the universe's expansion. Expansion also makes clear that relativity is not only a theory about fast objects or strong gravity. Special relativity begins with light and motion. General relativity begins with gravity and geometry. Cosmology asks what happens when geometry is applied to everything visible on the largest scale. The theory that explained Mercury's orbit and starlight near the Sun also allowed scientists to describe changing distances between galaxies across cosmic time. The scale can feel difficult, so the explanation should return to measurements. Cepheid variables gave distances, spectral lines gave redshifts, telescopes gave images and light, mathematical models gave possible histories. No one held the universe in the hand. No one watched space expanding directly in a single human moment. The conclusion came from many small signals arranged into a coherent pattern, with relativity providing the structure in which the pattern made sense. A galaxy far away sends light across expanding space. While that light travels, the scale of the universe changes, its wavelength stretches. Its arrival at Earth carries information from a time when the galaxy was younger and the universe was smaller. Looking outward becomes, in this sense, looking backward. Distance and time join again, not only in the moving train or the atomic clock, but across the history of the cosmos. The expanding universe widened the meaning of relativity. It showed that spacetime was not only curved near masses, not only stretched near black holes, not only measured differently by moving observers. Spacetime could have a large-scale history. Its geometry could change with time. The universe itself could be treated as a physical system, one with measurable structure rather than a silent container around everything else. From here, relativity begins to return toward everyday life in a surprising way. The same theory that describes galaxies and expansion also reaches into tools people use without thinking about curved spacetime at all. Clocks in orbit, satellites above Earth, and particles moving through machines all require relativistic corrections. The theory that changed the universe also lives inside modern precision. Chapter 13. Relativity inside modern life. Relativity can feel as if it belongs only to distant places. It appears near black holes, in the expansion of the universe, in light crossing intergalactic space, and in particles moving close to the speed of light. That reputation is understandable, because the strongest effects often appear where speeds are high, gravity is strong, or distances are large. Yet the theory also lives inside ordinary modern systems, not as a decoration, but as a correction required for precision. The easiest modern example is satellite navigation. A phone showing a location on a map seems to be using a familiar kind of technology: signals from satellites, a receiver in the hand, and software that calculates position. Underneath that simplicity is a timing problem. GPS depends on measuring how long radio signals take to travel from satellites to a receiver. Since radio signals move at the speed of light, even a very small timing error becomes a noticeable position error. The mistake of a few billionths of a second can matter. GPS satellites carry atomic clocks. These clocks are far more precise than ordinary watches, because the whole system depends on timekeeping. The receiver on Earth compares signals from multiple satellites and uses the timing differences to determine where it is. The satellites do not send down a little picture of the receiver's location, they send timing information, and the receiver solves a problem of distance from that information. The map on the screen depends on clocks in orbit. Relativity enters because those satellite clocks do not tick at exactly the same rate as clocks on Earth. Special relativity says that moving clocks run more slowly compared with clocks in the frame from which they are measured. A GPS satellite moves quickly around Earth, so its motion tends to make its clock tick slightly slower than a clock on the ground. General relativity says that clocks higher in a gravitational field tick faster than clocks deeper in gravity. Because GPS satellites orbit far above Earth's surface, this gravitational effect makes their clocks tick faster than clocks on the ground. The two effects work in opposite directions. The satellite's speed slows its clock relative to Earth clocks. Its weaker gravity speeds its clock relative to Earth clocks. For GPS satellites, the gravitational effect is larger, so the satellite clocks gain time overall compared with clocks on the ground. The difference is measured in microseconds per day, small by ordinary life but large for navigation. Without correction, GPS positions would drift by kilometers. This is a useful place to pause on scale. A microsecond is 1/1,000,000th of a second. Human attention cannot feel it. A conversation does not notice it. A footstep, a door closing, a hand reaching for a cup, and a glance at a screen all happen on timescales far larger than that, but light moves about 300 meters in 1 microsecond. For a system that measures distance by timing light speed signals, a tiny clock difference becomes a large distance error. Engineers therefore do not treat relativity as a philosophical curiosity. They build it into the system. Satellite clocks are adjusted before launch, and the navigation calculations account for relativistic effects during operation. The theory becomes part of ordinary infrastructure. A person following directions through a city may never think about curved spacetime, but the device in their hand is relying on it. The road, the satellite, the clock, and the signal are quietly tied together by relativity. This does not mean GPS proves relativity alone. The theory had already been tested in many ways. It means something more practical. A modern precision system fails without relativistic correction. Newtonian thinking alone is not enough once the clock differences become measurable and consequential. The theory has moved from blackboards and observatories into engineering, where being slightly wrong is not acceptable for long. Particle accelerators provide another everyday scientific use, though less visible to most people. In accelerators, charged particles are pushed to extremely high speeds by electromagnetic fields. As their speeds approach the speed of light, Newtonian formulas no longer describe their motion accurately. Adding energy does not keep increasing their speed in the simple old way. Much of the added energy increases their momentum and total energy while the speed approaches light speed without reaching it. Modern accelerators are designed with this in mind. The timing of fields, the curvature of particle paths, the energies of collisions, and the interpretation of the resulting particles all require relativity. A proton circulating in a large accelerator is not just a tiny bead moving quickly around a track. It is a relativistic particle whose energy, momentum, and lifetime must be understood through the rules that began with Einstein's fixed speed of light. Without those rules, the machines would not behave as intended. Muon experiments return here as well. Muons created in the atmosphere reach Earth's surface because of time dilation, and muons circulating in laboratory storage rings also reveal relativistic behavior. Their internal lifetimes, their motion through magnetic fields, and the measurements made from their decay all depend on special relativity. The particle does not announce that time has changed. The detector records counts, tracks, and energies, and the relativistic pattern appears in the numbers. Relativity also enters electronics and chemistry more than many people expect. In heavy atoms, electrons near the nucleus can move at speeds large enough for relativistic effects to influence their behavior. This affects the structure of certain elements and helps explain properties that would otherwise be harder to account for. Gold's color, for example, is influenced by relativistic effects in its electrons. Mercury's unusual liquid state at room temperature is also connected to relativistic changes in electron behavior. These examples are not as simple as GPS, because they belong to quantum chemistry as well as relativity. Still, they show that relativity is not confined to the very large. It reaches the very small when particles move fast enough or fields become strong enough. The same broad principle remains. Ordinary intuition comes from slow motion and weak gravity, while precise science must follow nature into regimes where those habits no longer suffice. Even electrical power systems and communication networks depend on precise timing, though not always in ways that require relativity as visibly as GPS does. The modern world has become a world of synchronized signals. Financial systems, telecommunications, scientific observatories, and navigation networks all need timekeeping at levels far beyond ordinary clocks. Relativity becomes relevant whenever height, motion, or gravitational differences are large enough for precision to notice them. Atomic clocks have made this especially clear. Place two highly precise clocks at different heights, and general relativity predicts that the higher clock will tick slightly faster because it is in a weaker gravitational field. Modern clocks have become so sensitive that they can detect time differences over surprisingly small height changes. A clock raised above another by a modest vertical distance can, in principle, accumulate a tiny measurable difference. Timekeeping has become a way of sensing gravity. This leads to a field sometimes called relativistic geodesy. Since clocks tick at rates affected by gravitational potential, precise clocks can help measure differences in height and Earth's gravitational field. The idea sounds strange only because ordinary clocks are too crude to show it. With enough precision, time itself becomes a measuring tool for the shape of Earth's gravity. A clock can become, in a quiet way, an instrument for reading position in a gravitational landscape. Relativity also matters in astronomy every day. Light from stars and galaxies can be shifted by motion, stretched by expansion, bent by gravity, delayed by passing near massive objects, and altered by gravitational fields. Astronomers account for these effects when interpreting observations. A telescope collects light, but relativity helps explain what happened to that light before it arrived. The image alone is not the full measurement. The path, the timing, and the shift all carry information. In binary pulsar systems, relativity becomes measurable through the timing of pulses. Pulsars are rotating neutron stars that send beams of radiation across space. If the beam crosses Earth, observers detect regular pulses, like the ticks of an astronomical clock. In systems where pulsars orbit other compact objects, the timing changes reveal relativistic effects, including orbital decay caused by gravitational wave emission. Long before direct gravitational wave detection, such systems gave strong indirect evidence that general relativity was describing real energy loss. The Hulse-Taylor binary pulsar, discovered in 1974, became one of the classic examples. Russell Hulse and Joseph Taylor found a pulsar in orbit with another neutron star. Over time, the orbit changed in a way consistent with the emission of gravitational waves predicted by general relativity. The system acted like a natural laboratory. No one built the neutron stars. No one controlled the orbit. Careful timing turned their motion into a test of gravity. Modern life also uses relativity in a more indirect cultural sense. It has changed the meaning of certainty about time. Before relativity, it was natural to think of time as the same everywhere and for everyone. Modern precision has made that idea less exact. Two clocks at different heights, two clocks in different states of motion, and two clocks following different paths can record slightly different elapsed times. This does not disturb ordinary life. It simply means ordinary life is not the whole scale of measurement. The same lesson applies to space. Rulers remain reliable in their own frames. Roads do not become uncertain. Buildings do not lose their dimensions. But when comparing frames moving close to light speed, length becomes frame dependent. In engineering on Earth, this rarely matters for solid objects. In particle physics and high-speed astronomy, it matters greatly. The theory waits quietly until the conditions call for it. There is comfort in this layered view of science. A person does not need general relativity to pour water into a glass. Newtonian mechanics can guide a bridge, a vehicle, or a falling object in ordinary conditions. Special relativity is needed for high speeds. General relativity is needed for strong gravity, precise clocks, and large-scale cosmology. The theories do not all compete in daily life. They nest, each one becoming necessary when the older approximation reaches its boundary. That nesting is why relativity does not make common sense worthless. It explains why common sense works so well in its own region. Human beings are slow compared with light. Earth's gravity is gentle compared with black holes. Most clocks in daily use are not precise enough to reveal gravitational time differences. The world feels Newtonian because the human scale sits in a place where Newton's picture is a very good approximation. Precision changes the world that can be seen. With atomic clocks, time becomes sensitive to height and motion. With satellites, small relativistic differences become navigation errors unless corrected. With accelerators, particles reveal energy and momentum relations far beyond Newtonian expectation. With telescopes, light carries records of gravity, motion, and expansion. Relativity is not far away from modern life. It is hidden inside the accuracy modern life has learned to demand. The theory that began by asking why light keeps the same speed now helps phones locate streets, laboratories guide particles, Astronomers read distant systems, and clocks measure gravity. It remains strange only if the old assumptions are treated as final. Once those assumptions are softened, relativity becomes a careful extension of measurement into places ordinary senses could not reach. It is not separate from the world people use. It is part of the world becoming precise. Yet even a theory this successful has edges. General relativity describes gravity with exceptional power, and special relativity remains woven into modern physics. Still, there are places where relativity meets questions it cannot answer alone. At the centers of black holes, in the earliest moments of the universe, and wherever gravity must be joined with quantum physics, the map becomes incomplete. The final chapter turns toward those edges, where relativity remains one of science's strongest guides, but not its last word. Chapter 14. Where relativity still waits, a successful theory does not have to be the final theory. This is one of the gentlest ways to understand the unfinished parts of relativity. Special relativity changed the meaning of time, distance, motion, and energy, and general relativity changed the meaning of gravity. Together, they have passed tests so precise that they belong among the strongest achievements in modern science. Yet the same theory that works with such care around planets, satellites, black holes, and gravitational waves reaches places where its own language becomes incomplete. The incompleteness is not a failure in the ordinary sense. A map can be accurate across a continent and still not describe the ocean floor. A clock can be precise for daily use and still not measure the smallest interval nature allows. Newtonian gravity remains useful because it describes weak gravity and slow motion with great accuracy. Relativity did not make Newton worthless. It showed the boundary of Newton's description. In the same way, a deeper theory may one day show the boundary of relativity without erasing what relativity already explains. The most important boundary lies where gravity meets quantum physics. Quantum theory describes the behavior of matter and energy at extremely small scales. It governs atoms, particles, fields, radiation, and the probabilities that appear in microscopic measurement. General relativity describes gravity as the curvature of spacetime, a smooth geometric structure shaped by mass and energy. Each theory works with great success in its own domain. The difficulty appears when nature asks for both at once. Most situations do not require that union. A planet orbiting the Sun can be described with gravity while ignoring quantum effects. An electron inside an atom can be described with quantum theory while ignoring its tiny gravitational influence. The separation is usually safe because gravity is weak at microscopic scales, and quantum effects usually average away at astronomical scales. Nature often allows scientists to use one description at a time. The trouble begins in extreme places. The center of a black hole is one such place. General relativity, followed inward, points toward a singularity, a region where the classical description says curvature becomes unbounded and ordinary paths through spacetime cannot be continued. That result is not usually treated as a complete physical object waiting at the center. It is a sign that the theory has been pushed beyond the range where its smooth geometry can be trusted alone. At such scales, quantum effects should matter, but general relativity does not contain them in the needed way. The earliest moments of the universe raise a similar difficulty. If the expanding universe is traced backward, the cosmos becomes hotter, denser, and smaller in the description. General relativity guides much of that history, and modern cosmology has built a strong account of the early universe after its first extremely brief intervals. But at the very beginning, where density and curvature become extreme, the theory reaches conditions where quantum gravity should be needed. The map again becomes incomplete at the edge of its own precision. Quantum gravity is the name for the hoped-for deeper description. It is not one settled theory. It is a research goal and a family of approaches. Some physicists study string theory, where the basic ingredients of nature are not point-like particles but tiny extended objects whose vibrations correspond to different particles. Others study loop quantum gravity, where space-time geometry itself may have a discrete structure at the smallest scales. Other approaches use different tools, including quantum field theory, holography, causal sets, and modified ideas about spacetime. These approaches should be spoken of carefully. They are not all established in the same way relativity is established. They are attempts to solve a real problem: how to make gravity and quantum physics belong to one coherent description. Some have deep mathematical power. Some connect to black hole thermodynamics, particle physics, or cosmology. None has yet replaced general relativity with a fully confirmed theory tested across the necessary range. The frontier remains open. Black holes sharpen the frontier through information. In ordinary quantum physics, information about the state of a system is not meant to disappear from the universe's bookkeeping. Black holes, however, seem to hide information behind horizons, and Stephen Hawking's work in the 1970s showed that black holes should emit radiation due to quantum effects near the horizon. If a black hole slowly loses mass through this radiation and eventually evaporates, a question appears: what happens to the information about what fell in? This is the black hole information problem. It is not a simple puzzle about messages or memory in the everyday sense. It concerns the consistency between quantum theory, gravity, horizons, and radiation. If information is destroyed, quantum theory needs revision. If information escapes, then the way it escapes must be explained without violating the structure of spacetime that general relativity provides. The problem remains one of the places where the two great frameworks press most strongly against each other. Hawking radiation itself also shows how the edge of relativity can be productive. General relativity supplies the black hole background. Quantum theory supplies the behavior of fields near the horizon. When the two are used together in a limited way, they suggest that black holes are not perfectly black and that they have a temperature. This does not yet give a complete quantum theory of gravity, but it shows that the frontier can produce meaningful results even before the final theory exists. Gravitational waves offer a different kind of edge, one where relativity has been confirmed with unusual strength. General relativity predicts that accelerating masses can create ripples in spacetime, carrying energy outward. For decades, these waves were inferred indirectly, especially through the changing orbit of the Hulse-Taylor binary pulsar. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves directly from the merger of two black holes. The signal matched the pattern predicted by general relativity. That detection did not expose a failure. It showed the theory working in a violent and strong field regime far beyond the solar system tests that first supported it. Two black holes, each many times the mass of the Sun, merged more than 1 billion light-years away, and the resulting change in distance measured by LIGO's detectors was smaller than the width of a proton. The event was distant, but the measurement was local, recorded by laser beams traveling through long vacuum arms on Earth. LIGO's detection also opened gravitational wave astronomy. Telescopes observe light and other electromagnetic radiation. Gravitational wave detectors observe changes in spacetime itself, produced by massive accelerating systems. Black hole mergers, neutron star mergers, and other compact object events can now be studied through these signals. Relativity, once tested through Mercury and eclipses, became a working language for a new kind of observation. Still, even these confirmations do not close the frontier. They make the frontier sharper. The more accurately relativity succeeds, the more clearly scientists can ask where deviations might appear. Future detectors may test gravity in new regimes. Observations of black holes may constrain alternative theories. Precision clocks may reveal tiny effects. Cosmology may show whether the large-scale acceleration of the universe is best described by a cosmological constant, a new field, or something more unexpected. Dark energy belongs to this open region. The observed accelerated expansion of the universe can be modeled within general relativity by including a cosmological constant. That is the simplest fit in the standard cosmological model, but the physical nature of dark energy remains uncertain. It may be vacuum energy. It may be something dynamic. It may point toward a deeper issue in the relation between quantum fields and spacetime. Relativity gives the framework in which the expansion is described, but the content behind the acceleration is still under study. Dark matter is another part of the larger gravitational picture. though it is not a failure of relativity by itself. Galaxies and galaxy clusters behave as if more mass is present than the visible matter supplies. Gravitational lensing, galaxy rotation curves, and the cosmic microwave background all support the presence of unseen mass. Most evidence points toward dark matter as some form of matter not yet directly identified. Some alternative theories try to modify gravity instead. Relativity remains the foundation for much of the analysis, while the missing substance has not yet been detected in a final way. This is how mature science often looks. It is not a clean row of finished answers followed by ignorance. It is a layered structure with reliable knowledge, active measurement, working models, and open questions all present together. Relativity is reliable in the domains where it has been tested. It is incomplete where quantum gravity is required. It is actively used where cosmic expansion, lensing, black holes, and gravitational waves are measured. The theory is not fading at its edges. It is still organizing the questions asked there. For someone who began with confusion, the path can now be simplified. Special relativity began by taking the speed of light seriously. If light's speed is fixed for all steady observers, then time and distance must change between frames. General relativity began by taking gravity and acceleration seriously. If falling can locally remove the feeling of gravity, then gravity is not merely an ordinary force but part of the geometry of spacetime. From those two beginnings came time dilation, length contraction, mass-energy equivalence, curved spacetime, light bending, black holes, cosmic expansion, satellite corrections, and gravitational waves. The open questions do not undo that path. They show where it continues. A theory that began with clocks and light now points toward the smallest structure of spacetime and the largest history of the universe. It tells engineers how to correct satellite clocks, tells astronomers how light bends near galaxies, tells physicists what signals to expect when black holes merge, and tells cosmologists how expansion can be described. Where it cannot yet speak fully, it leaves a clean outline of the missing language. Relativity still waits at those edges. It waits where a black hole horizon meets quantum information. It waits where the early universe becomes too dense for classical geometry alone. It waits where dark energy keeps the cosmic expansion accelerating. It waits inside detectors, listening for spacetime's faint changes, inside clocks precise enough to measure gravity through time, and inside theories still searching for a union that has not yet settled. The story, therefore, does not end with relativity being simple in the ordinary sense. It ends with relativity becoming understandable. Time is not one universal flow. Space is not one fixed stage. Light is the rule that forces clocks and rulers to adjust. Gravity is geometry, not merely a pull. Mass and energy are linked. The universe can expand. Clocks in orbit must be corrected. Black holes can exist because spacetime can curve so severely that all future paths inside a boundary lead inward. Once those ideas are placed slowly, the confusion loses some of its sharpness. Relativity remains deep, but it no longer has to feel like a riddle. It becomes a careful description of a world where ordinary experience is true enough for ordinary life, and yet not wide enough for nature as a whole. A clock on the ground, a satellite above Earth, a beam of light crossing space, and a wave passing through a detector all belong to the same larger order. Far from the first moving train and the first question about light, the theory continues in measured corrections and open problems. It remains in the tick of clocks at different heights, in the paths of photons near galaxies, in the timing of pulsars, and in the faint signals from black holes that merged long before the light from many nearby stars began its journey. The world does not need to announce this structure for it to be present. Time keeps passing along different paths, and each clock, wherever it is, records the path it has been given. A theory can travel a long way from the question that first opened it. Relativity began with light, clocks, motion, and the quiet difficulty of making measurements agree. It moved from trains and platforms to particles and satellites, from falling elevators to curved spacetime, from Mercury's orbit to eclipses, black holes, gravitational waves and the slow expansion of the universe. Yet, underneath the reach of it, the first discipline remains simple. Nature is measured carefully, and the measurements are allowed to change the picture. The world still looks ordinary because ordinary life is allowed to be ordinary. A clock on a wall keeps its familiar rhythm. A road holds its length. A stone falls. A room remains where it is. Nothing in daily experience needs to announce curved spacetime or the fixed speed of light. The older habits continue to work across the scale where human bodies live, because the differences are usually too small to feel. Above Earth, a satellite clock keeps a slightly different account. In a laboratory, a particle moving near light speed carries time differently from a particle at rest. Near a galaxy, a path of light curves through a geometry shaped by mass. Far away, two black holes that once circled one another leave a faint change in spacetime, and long afterward, a detector measures the passing strain. Each case belongs to the same patient structure. Relativity does not remove steadiness from the world. It places steadiness inside a larger order. Time passes along paths. Clocks record those paths. Light keeps its speed. Gravity shapes the geometry in which motion unfolds. The universe expands, not as a thing flying into empty space, but as distances changing with the scale of space itself. None of this has to be felt directly for it to be true. A person resting under Earth's gentle gravity remains inside the same universe as the satellite, the muon, the distant galaxy, and the old beam of starlight bent near the sun. The differences are matters of speed, height, mass, distance, and precision. At one scale, the world is familiar enough to live in without calculation. At another, the hidden corrections become measurable, and the familiar world opens into a deeper arrangement. There is no need for the mind to hold all of it at once. The theory remains whether it is remembered or not. A clock continues to count its own path. A signal moves from satellite to ground. A photon travels across space. A planet follows its orbit. The geometry around Earth keeps its mild curve, and higher above the surface, time keeps its slightly quicker pace. Relativity leaves the world not less real, but more carefully described. The ordinary day remains, with its rooms, roads, clocks, and shadows. Beyond them, and quietly within them, the deeper rules continue. Light moves at its fixed speed. Gravity shapes the paths available. Time gathers differently along different routes, and everywhere, without needing to be noticed. Each clock keeps the time that belongs to where it has been. The journey is complete. Rest well.